Inside a chunk of diamond smaller than your fingernail, scientists have just discovered something that shouldn't exist. Not just a new material, a new phase of matter, and it breaks the very rules of time itself. The biggest problem is, no one fully understands how it works yet, not even the people who made it. So, let's take a peek and try to figure it out. The story started over a decade ago. Scientists created the first time crystal. Sounds like some mysterious component for a time machine, but it's something even weirder. Take a regular crystal and check it out under a microscope. Like everything around us, it consists of molecules and atoms. What makes crystals special is that their atoms are arranged in a repeating pattern. A salt crystal, for example. If we look at it, we'll see a repeating pattern inside it. And this pattern is the same everywhere, no matter how large or small the piece of salt is, or what shape it is. In the whole crystal, it's unchanged, and it will remain the same no matter how much time has passed. You might also know that all the atoms around us are constantly moving, even at very, very low temperatures when everything freezes and nothing can stop them. Their movement is random, chaotic, and unpredictable. They're just jiggling in space. But time crystals have their own special quirk. Not only are their atoms arranged in the same pattern, just like regular crystals, but these atoms also moved in a looped, endlessly repeating dance. It's super weird. The atoms in time crystals are like an endless dance party. All the guests repeat the same moves in the same order over and over again. The movements in these dances can be basic and simple, or overly complex and chaotic, but they're always looped in time, hence the name. Now, just to clarify, these crystals aren't the kind we're used to. They don't look like gems, diamonds, emeralds, or anything like that. Actually, they don't look like much at all. The beautiful name time crystal describes a new, very strange kind of matter that changes in quantum states, which is what we call the weirdly looped dancing atoms. But even after scientists discovered them, there was something even crazier about them. These dance movements, for some reason, persist even at absolute zero temperature. In all normal materials and objects, if we cool atoms down to such a crazy degree, they would freeze, lose energy, and stop moving. In time crystals, they continue their endless dance as if nothing happened. Oh, and that was only the beginning. Scientists also got stunned because the existence of time crystals seemed to violate the second law of thermodynamics. Now, this law states that over time, any system becomes random and distorted. For example, a warm coffee will distribute its heat and become cold. Ice dropped in the water will eventually melt and unite with it, making water colder, and so on. At first, they thought that time crystals broke this law because it seemed like their atoms can move indefinitely, like a perpetual motion machine. It seemed like not only do they move constantly in the same pattern no matter what happens to them, but they don't need any energy to do so. But then it turned out that they do require energy after all, either from lasers or magnetic fields. So even though they're little marvels, they don't break our physics laws, yet. There were theories that this stuff could exist. Time crystals were first predicted in 2012 by a theoretical physicist, Frank Wilczek. Not all physicists accepted the theory at the time. Many believed that the crystals would violate the second law of thermodynamics, which means breaking physics. But the universe really doesn't care what scientists think, and Frank Wilczek won a Nobel Prize for one of his works. Still, some scientists were skeptical about this until time crystals were invented for the first time in 2016. Research from the University of Maryland managed to create one. They did it like this. First, they took a regular crystal and cooled down the atoms inside it to near absolute zero, almost stopping them. Then they started shocking these atoms with lasers and made the atoms switch between different states repeatedly without absorbing any energy from the laser. You could say that the laser gave them a beat and made them dance by themselves without anyone's help. The result was the first time crystal ever. This was an amazing breakthrough, and ever since then, physicists kept studying time crystals to see what else these guys could do. The biggest problem was that such perpetual motion only truly exists forever in ideal time crystals. And since the time crystals in our experiments weren't ideal, they lasted only a few minutes before they melted and started behaving like regular matter again. But that didn't stop scientists. They wanted to make time crystals stable and usable. In 2021, they made another breakthrough. Researchers at Google collaborated with a bunch of big universities and used Google's quantum computer to create a much bigger and much more stable time crystal. If we manage to implement this property, these crystals could help us get closer to full-fledged, usable quantum computers. One of the biggest problems for this technology was memory. But the loop dances in time crystals might help us store information on a quantum level. That would be absolutely insane. Now, another thing scientists aimed at was a new kind of ultra-precise clock. Time crystals could also help us with that. And now, in 2025, they finally achieved big new successes. They took time crystals even further and created a time quasi-crystal. It's like the jazz version of a time crystal, more complex, a bit more chaotic, yet still coherent and weirdly beautiful. A team led by the researcher Chong Zhu created an atoms dance that was based on the golden ratio, the same perfect number we see in nature, in seashell spirals and sunflowers. In most time crystals, atoms dance to a simple beat like tick-tock, tick-tock. In time quasi-crystals, they gave these guys a melody in Phrygian scale over a Fibonacci-timed beat. In simple words, their movements became complex, not looping anymore, yet it still feels like actual structured dance, not random noise. Like a mosaic where no tiles repeat exactly, but still form a wonderful pattern. They started with a tiny chunk of diamond. Then they started hitting it with high-energy nitrogen atoms, knocking some of the diamond's carbon atoms out of place. That left behind empty pockets. Electrons rushed in to fill them, creating little quantum systems inside the diamond. Each of these pockets was highly microscopic, and the final system had over 1 million of them interacting together. Then came the microwaves. Using the magic of 2 overlapping pulses and golden ratio, they stirred the quantum particles into this bizarre, orderly, not looped time rhythm. And just like that, the time quasi-crystal was born. What they got was a stable, non-repeating atomic rhythm in time, something that, mathematically speaking, shouldn't be possible. And it's an entirely new phase of matter. So this isn't just a cool physics trick. It's a doorway into a part of the quantum world we barely understand. Normally, when you pump energy into a system, it either settles into a pattern or falls apart in chaos. But this one did neither. It found a new kind of order. But more than that, it might unlock technologies we haven't even dreamed of yet. Quantum systems like this could be shockingly stable, which is gold for quantum computers. Finally, quantum memory is on the horizon. Quantum computers could use these time quasi-crystals to store data long-term. Next, quantum sensors could use their incredible sensitivity to detect even the tiniest changes in the environment. And finally, the ultra clock we mentioned before, it's coming too. These crystals would help timekeeping devices be ultra-precise. Of course, we don't need this in daily life, but it will be incredibly useful in science. Strangely enough, it turns out that the same fragility that made these crystals difficult to handle also made them perfectly tuned detectors. All this is theory for now, but as scientists continue to study this, some usable tech might not be far behind.
Recently, Chinese scientists discovered something interesting on the moon, an unusual crystal. Moreover, they found out that this crystal contains an element that can literally replace nuclear fuel. Let's find out more. The composition of the moon has long remained a mystery to us. Half a century has already passed since the Apollo mission. Unfortunately, we haven't traveled to the moon much since then. So it's not surprising that it's not so easy for us to study it. But recently, we've made a breakthrough in this area. In December 2020, Chinese scientists sent the Chang'e 5 probe to the moon. The mission was named after the ancient Chinese deity of the moon, Chang'e. Quite poetic, isn't it? Anyway, after the probe went to the nearest side of the moon, it spent several days digging through the surface and rocks and then returned to Earth. In total, it collected about 4 pounds of various lunar rocks, like basalt, solidified lava, and so on. And yeah, maybe it doesn't sound too impressive, but it's actually a mini breakthrough. After all, we hadn't received any lunar samples since 1976. And these samples are very important for learning the history of our world. We've been struggling for many years to find out, for example, how the moon was born at all. Yes, there were a lot of theories, but we still couldn't find any proper evidence for any of them. But thanks to the latest missions and some computer simulations, scientists finally found out the truth. The moon was born when some random dwarf planet crashed into our Earth many millions of years ago. This dwarf planet was slightly smaller than Mars. The fragments of the Earth went into space, but some of them stayed in our orbit. Then they stuck together and formed the moon. It sounds horrifying, but in reality, the birth of the moon was the best thing to ever happen to our planet. If it weren't for this beautiful satellite, all our oceans would be small puddles. Life wouldn't have appeared on Earth at all. So this is already an amazing discovery, but that's still not all. Studying the collected rocks, scientists from the Beijing Research Institute discovered something unusual. A rare lunar crystal. Looks pretty boring, doesn't it? Just some tiny transparent monocrystal about the thickness of a human hair. We've already found such things on the moon before. These crystals were formed as a result of volcanic activity, just like some garnets on the Earth. And yep, the place where they discovered these crystals also suffered from volcanoes 1.2 billion years ago. That means that this tiny baby is over 1 billion years old. But that's not the most important thing. It's the fact that this crystal is made of a unique material, the one that we've never seen before. Researchers from the International Mineralogical Association have confirmed that such a composition can't be found anywhere on Earth. The crystal was named Chang'e, again after the same moon deity. And this is another achievement. This is the 6th previously unknown mineral that we've found on the moon and the first one found by China. Now, it has become the 3rd country in the world to make such a lunar discovery. However, this tiny crystal still wasn't the only remarkable thing they found. After studying this gem and about 140,000 other lunar particles, scientists have discovered something else. They found helium-3. Why is it so important? Because this is one of the elements that feed the sun and other stars in our universe. We tend to say stuff like, put out the sun is burning, and so on. And this is one of the reasons why many people actually think that the sun is a huge fireball. But it's not. Its burning is actually a completely different process, which is called nuclear fusion. The process itself is quite simple. During this reaction, hydrogen in the star turns into helium. But this simple process is actually one of the most violent and insane reactions in the universe. There's a real boiling broth of particles inside the sun. The hydrogen nuclei that jump and rush there are constantly repelling each other since all of them are positively charged. And so they could continue to boil and chill around without bothering anyone if it weren't for the stars. The stars turned out to be cheaters. They have such strong gravity that they basically grab billions of these little atoms and squeeze them together. Combining with each other, these atoms create new heavy elements, like the mentioned helium. And when this happens, they throw a lot of energy into space. And that's how the sun burns. At the same time, it spreads so much energy that we can't even imagine. Okay, so what is helium-3? Well, this is an element to which even the sun can say, "Whoa dude, you should calm down." The fusion of helium-3 atoms releases even more energy than in typical nuclear fusion. And most importantly, it doesn't pollute the atmosphere with harmful things like radiation. We have very, very little helium-3 on Earth. Its prevalence in our atmosphere is about 1 in a million. And besides, it's constantly trying to escape from us back into space. Probably feels some bad vibes from us. However, scientists have recently found out that there's a place that contains a lot of this element. Yep, you guessed it, it's the moon. We think that there's more helium-3 on the moon than on Earth because of the solar winds. The sun has been hammering on the moon with its helium-3 for billions of years, so now it's all over the place. It's still not too much if you compare it, for example, with Jupiter or Saturn. But don't forget how much energy it can release. For your information, with only 25 tons of helium-3, it's possible to provide America with energy for an entire year. Now, there are 35,000 tons of it here on Earth, and more than 1 million tons on the moon. Only these sources could feed the entire US for thousands of years. So basically, in the future, helium-3 may become a new source of fuel. And it's better than nuclear fuel in basically everything. Helium-3 won't leave any harmful waste and radiation. It's more powerful and not that dangerous. In other words, this environmentally friendly and efficient energy could be a revolution for our planet. Sounds cool, huh? So, what are we waiting for? Grab the shovels, you might say. But there's a little problem here. Unfortunately, we haven't yet come up with anything as wildly strong and hot as the stars. To use helium-3, we need crazy temperatures and pressure. We need a thermonuclear reactor, and we have no idea how to build it, yet. And even if we could heat it up to such temperatures and get the needed pressure, we still don't really know how to handle helium-3 correctly. Therefore, even if we have an infinite amount of helium-3, we still won't be able to use it. But still, there's a great power behind helium-3, so it's not surprising that different countries have already started a race for nuclear resources. Now that Chang'e 5 has discovered a new helium-3 deposit on the nearest side of the moon, this race can become downright global. For example, China already plans a new lunar mission in 2024, Chang'e 6. During this mission, they want to collect the first samples from the far side of the moon. As you can see, finding this lunar crystal was very important for us. These crystals can help us find new ways to create helium-3. And if we manage to do that, humankind will enter a new era. But to do this, we still have to solve a number of problems. How to deliver a bunch of these lunar crystals to Earth, how to make them produce energy, and so on. Let's hope that in the future these issues will be resolved and we'll find a way to produce clean, safe, unlimited energy. The morning is cloudy, but it isn't raining. So you grab your bag and head off to work. You're halfway there when it starts drizzling, then raining, then pouring. There's only one thought in your head as you're dashing through wet streets towards your office building. If only I could hop in a time machine and go back in time. I'd have put that umbrella in my bag. Unfortunately, going back in time is not possible. But guess what? We still managed to travel in time. But let's start from the very beginning. More than 100 years ago, a famous scientist called Albert Einstein, I bet you've seen his most popular photo, came up with a theory about how time works. He gave it a nice little scientific name, the theory of relativity. According to it, space and time are linked together. Another point is that our universe has a set speed limit. Nothing can move faster than the speed of light, which is 186,000 miles per second. Okay, you may say, but what does it have to do with time travel? Well, the theory of relativity also claims that the faster you move, the slower you experience time. And several experiments prove this to be true. For example, let's say you have two clocks set to the exact same time. You leave one clock at home and take another one with you while traveling by plane. What's important here is the fact that the plane is going in the same direction as Earth. After your plane finishes its flight around the world, you can compare the time on the two clocks. You find out that the clock that traveled with you is a bit behind the clock that remained on the ground. Because of this, GPS clocks are corrected. GPS satellites travel around our planet at tremendous speeds, around 8,700 miles per hour, and more than 12,000 miles above the surface of Earth. This speed slows GPS satellite clocks down, but the altitude speeds them up. As a result, the clocks on GPS satellites experience time at a rate that is slightly faster than 1 second per second. And if this difference in time wasn't corrected, you wouldn't be able to use GPS to figure out your exact location. In any case, this is probably the closest thing we have to time travel. You see, our planet is constantly moving around the Sun at an average speed of 67,000 miles per hour. The Sun, along with the entire solar system, is, in turn, circling the center of our home Milky Way galaxy at a staggering 140 miles per second. And the Milky Way itself is also moving. It's spinning at a speed of 130 miles per second. Those are some really dizzying numbers. And now imagine that in order to get to the past, all this space matter must also turn back and return to its original position. Just admit it, it's absolutely impossible. By the way, even though we can't exactly travel back in time, we can look at the past, thanks to NASA's space telescopes. They help us see stars and galaxies that are insanely far away. It takes the light coming from them ages to reach Earth. That's why when you observe those distant worlds, you see what they looked like a long time ago. Now, what if time travel was somehow possible? Wouldn't all the fun be spoiled by the time travel paradox? You know, like finding yourself in the past and accidentally preventing your parents from meeting each other? The problem is that Einstein's theory of general relativity theoretically allows a person to travel back in time and come in contact with their past self, which can potentially endanger their existence. But you can breathe out. Some scientists at the University of Queensland have recently claimed that this paradox might not actually exist. They say that even if you made some changes in the past, the timeline would self-correct anyway. In other words, it would still ensure that whatever event sent you back in time would still happen. One more study claims that even if some changes happened in the past, they wouldn't drastically alter the future.
Okay, so you've seen the movies and read the books on time travel. Most of them tell stories about entering some futuristic boxes, and in the blink of an eye, you're in some different epoch. For now, this is just sci-fi. But there are ways to make time travel possible, at least theoretically. We just don't have the technology figured out yet. For starters, time travel to the future could be achieved by traveling at high speeds, but not just getting a ticket on the superhighway kind of speed. This is based on Einstein's theory of special relativity. It explains that time slows down for objects that move at really high speeds. And the good news is scientists have already tested this theory, and it looks promising. They did it with the help of two identical clocks. One was placed on a jet, and one stayed on the ground. They found that the clock on the jet ticked slower than the one on the ground because of how fast the jet was moving. The faster an object is moving, the more time will slow down for it. Currently, the fastest speeds achieved by human technology are seen in a special type of particles called neutrinos. Some of these can move at almost the speed of light. At these speeds, 1 second for the protons is equal to 11 months for us. Now, we might be able to time travel to the future with the use of gravity, too. This idea is based on Einstein's findings, namely his theory of general relativity. Now, this theory explains that the stronger gravity is, the more slowly time moves. This means that as you get closer to the center of the Earth, the strength of gravity increases. And if you think about it like that, time actually passes more slowly for your feet than for your head. Now, is that why I'm always late for stuff? Good excuse. This effect has been measured too, with the help of the same strategy with two identical clocks. Scientists placed them on shelves at different heights and measured the rate of ticking. The clock on the lower shelf ticked more slowly because it experienced a slightly stronger gravity. But this option comes with a catch. To be able to travel to the far future, you'll need to find a place with extremely strong gravity, like a black hole. That's a point in space where the gravity has so much force that even light cannot escape it. There, gravity becomes so intense that matter gets squeezed into a tiny space. The closer you get to the black hole, the more slowly time moves. However, traveling via a black hole is very dangerous, mostly because it's a one-way ticket. Once you cross its edges, there's no coming back. Now, here's a fun fact. The GPS systems we use on our phones and in our cars already have to account for time dilation effects in order to work properly. That's because of the speed of the satellites they use and the gravity they feel here on Earth. Without these corrections, your phone's GPS wouldn't be able to pinpoint your location on Earth very precisely. Meanwhile, the third option has less to do with the universe's unknown forces and more to do with our own bodies. Scientists are trying to find ways to time travel to the future by slowing down the body's own processes. It's not time travel per se. You wouldn't technically be going anywhere. But if your body stays put for a long period of time, you could eventually wake up in the future. Some animals, like bears and squirrels, can slow down their metabolism during hibernation, which means they don't need as much food and oxygen to survive. Specialists are trying to figure out if humans can do the same thing. They're working on ways to make people go into a short-term hibernation for a few hours to begin with. This could be helpful for medical emergencies too, in order to help a person before they can safely get to the hospital. In 2005, scientists were able to slow down the metabolism of mice by exposing them to a small amount of special gas. However, when they tried to do the same thing with larger animals, it did not work as effectively. Our fourth option of traveling through time is really unique. It involves a special type of shortcuts that may exist in our universe called wormholes. Now, before we move on, let's try to understand what they are. You'll need to picture two balls and a trampoline. If there's no pressure applied on the trampoline, it stays flat. Now imagine the two balls placed on the trampoline symmetrically. If you look at them from this perspective, there's no possibility of them ever touching. But if you put enough pressure on the trampoline between the two balls, this flexible fabric can stretch so much that the two objects might potentially touch each other. The same thing happens with stars in different star systems. They're big enough to curve space around them. That's why most planets tend to orbit around a star. The tunnel between those 2 points would be a wormhole. These wormholes could be used to travel long distances, like 1 billion light years, or even visit different times. Now, many scientists, like Stephen Hawking, think that wormholes might appear and disappear, but be very small, smaller than atoms. The problem is that we don't know how to catch one and make it bigger so that people can use it. This would take a lot of energy, and we don't know if it's even possible. Some astronomers say that even if we could find a wormhole and enter it, it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole slamming shut, like a rubber band that's been stretched too much. Now, the fifth solution for time traveling was proposed by an American physicist named Ron Mallett. It involves one resource that we know for sure is abundant in the universe: light. The scientist proposed a theory about time travel that would use a rotating cylinder of light. He believes that if something was dropped inside this swirling cylinder, it could be moved in both space and time, similar to how a bubble moves when you swirl it with a spoon in your coffee. According to Mallett, the right shape of the cylinder could allow for traveling to both the past and the future. The physicist has been trying to raise money for an experiment to test his theory. This experiment involves dropping tiny particles, called neutrons, through a circular arrangement of spinning lasers. However, other scientists say Mallett's theory is impossible and there's no need to test it further. Well, even if we eventually figured out a way to travel back in the past or to the future, would it be safe? Scientists have been talking about a problem called the paradox of time travel for a long time. The main question is what would happen if you went back in time and did something that changed the future. However, a new study from researchers from the University of Queensland says that this problem might not be real after all. The scientists have done some calculations and found out that even if you had changed something in the past, the timeline would still end up the same way. Another variation of this problem is called the grandfather paradox. Imagine going back in time and preventing your own grandfather from having offspring. Come to think of it, it automatically means you shouldn't exist in the first place. If your grandparents didn't have your parents, how can you exist at all? Well, these days scientists are certain that even if you did experience something like that, you'd still exist in the present. That's because the timeline that already exists has a way of adjusting itself, regardless of where people are in time and what they do. Or somehow get 1.21 gigawatts in a DeLorean and make like Marty McFly.
Time runs like a river. It has direction, always advancing. It has a certain duration, periods between events you can measure. Time feels real, always there, unstoppable, moving forward. But what if I told you that time might not exist? Some physicists and philosophers claim that there might be no such concept as time, and we should take this possibility of the non-existence of time seriously. You see, recently physics has been in crisis. For the past century or so, two extremely successful physical theories have been used to explain the universe. Those are the theory of general relativity and quantum mechanics. Quantum mechanics describes how things work in the super tiny world of particles and their interactions. As for general relativity, it provides an outlook on the bigger picture, for example, gravity or how objects move in space. And even though both of these theories seem to be working really well, they are believed to conflict with one another. That's why some scientists think that they need to be replaced with a new, more general theory, like quantum gravity. This idea might be able to explain how gravity works at the miniature scale of particles. Apparently, it's incredibly difficult to produce the theory of quantum gravity, but it might be possible to do it with the help of string theory. It replaces particles with strings, vibrating in 11 dimensions. But there's one problem. Even though string theories do provide several models describing the universe, they don't make any clear predictions that can be tested by experiments to understand which model is the correct one. There's one more idea known as loop quantum gravity. According to it, the fabric of space and time is made of super tiny chunks, loops. But the most remarkable aspect of this theory is that it completely eliminates the concept of time. Now suppose this idea turns out to be correct. Will it mean that time doesn't exist? Well, the answer is kinda complicated. Everything depends on what the word exist means. A philosophy professor from Cambridge University claims that the three basic properties of time, a present moment that is special, the flow of time, and its direction, come from our mental states and not from the physical world. So we sense this arrow of time because our minds add a certain subjective ingredient to reality. At the same time, Einstein's theory of relativity supports the idea of the block universe, a four-dimensional space-time structure where time is like space. It has its own coordinates in space-time. Time is tenseless there. Thus, the future and past are as real as the present. Does it mean we're being fooled by our human perspectives? Is the feeling that time passes and has a certain direction false? Well, we can imagine our world as a three-dimensional place where stuff happens gradually over time. Or it might be a four-dimensional space where nothing actually happens because nothing changes. It's all here at the same time, past, present, and future. The main idea of relativity is that there's no absolute space and no absolute time. Everything is relative. Trying to think about time in the context of the universe, you realize that you need to isolate part of it and call it, let's say, your watch. And time is basically the relationship between some parts of the universe and that thing you called your watch. Another scientist says that time is just a collection of snapshots describing our reality while continuously changing one into another. Here, you hit play. Here, you're blinking while watching this video. And here, you're taking a sip of your coffee. Without these changes, there wouldn't be any notion of time. The changes are real, but time is not. Our brain sees these changes and constructs a sense of time, believing that it's flowing. What do you think? Is time just a social construct, or does it really exist?
Now, did you know that there's an astronomical object in which space and time actually swap places? How does that work? And what exactly does swapping space and time mean? Well, let's figure it out. Imagine that you're on a spacecraft. The vehicle can only move straight. Your path leads to some inevitable point, and you have no idea what lies ahead. You can only hope that it won't be too bad. Meanwhile, everything around you is complete madness. A chaotic collage of many historical events. What do you see? Ancient humans and dinosaurs? The birth of the universe? Future? Who knows? That's what the universe would look like if we swapped time and space. And theoretically, this is what you would see if you fell into a black hole and somehow were able to survive. But how is something like this even possible? First of all, let's discuss time and space. Imagine drawing a light bulb on a sheet of paper. Then grab one more sheet and draw how it lit up. Right now, it's just a small circle of light. Another sheet, the circle of light is growing. It gets bigger and bigger in size until finally it turns into a giant circle. In real life, the bulb lights up in the blink of an eye. That's because the speed of light is the fastest in the universe. But here, on our drawings, we capture the propagation of light frame by frame. We see how over time the light has grown from a small dot to a large circle. But if you connect these circles, doesn't it remind you of some shape? For example, a cone? Yes, exactly. This is called a light cone, and time is the central axis of this cone. Why? Because light turns from a small dot into a large circle over time. To remember it, let's draw a time vector, an arrow inside the cone. It goes from the past to the future. Meanwhile, the circles are space. In space, we can move however we want, in any direction. We can move up or down, in zigzags, and so on. But no matter what zigzags we draw along the timeline, we're always moving forward. We can't turn back in time, and we can't stop it. This helps us define time and space. Time is the direction in which the light cone is oriented. This is the direction where all our paths lead, and where our future inevitably lies. And space is the whole variety of directions perpendicular to the timeline. This is a straightforward graph. If it could be applied to the entire universe, then time would flow the same everywhere. However, if you've watched at least some popular sci-fi movies, you know that this isn't the case. In reality, time can be crazy. For example, if you're chilling near a black hole, what will be 2 hours for you may turn out to be 20 years for your friend on Earth. But why? Well, take a deep breath. Now, gravity comes into play. Oh, I know about gravity. It's that thing that helps me to stand on the ground, you may think. But it's much, much more complicated than that. Gravity is one of the basic physical forces in our world, and it's incredibly powerful. In fact, she's such a girl boss that she can distort space and time. She can literally influence the speed of time like an almighty wizard. How? Well, let's take something slightly bigger than a light bulb. For example, a supernova. Somewhere in the universe, a star has just made a boom. How do we know about it? Well, nothing in the universe, no sound, no radio waves, nothing, travels faster than light. So we'll know about the birth of a supernova only when we see it. And this will happen only when its light cone grows enough and reaches our planet. So the light cone grows and grows. So far, everything is fine. And finally, it reaches our planet. But there's a catch. You see, our planet is very massive, and it has pretty strong gravity. What happens then? Gravity changes the direction of the light cone. It begins to attract the cone to the center of our planet, and with it, it also attracts our arrow of time. That means it slows the time down, and the closer the light cone is to us, the more the arrow bends and the slower time goes. What does it mean? Well, for example, the fact that the watch on your ankle will lag behind the watch on your wrist, that your head is aging faster than your legs, and that astronauts in Earth's orbit age a little slower than people on Earth. This is what scientists call general relativity. Right. But how does this relate to our topic? How can we understand what will happen if we swap space and time? Don't worry, we're almost there. Now, imagine a cosmic body with incredibly strong gravity. It bends time and space so much that it feels like they swap. This is a black hole. A black hole attracts absolutely everything to its center. No stars, planets, no light can escape from there. Let's say our light cone is approaching it. First, as usual, time begins to bend toward the center of the black hole, attracted by its gravity. But the gravity is very strong, so it bends more and more, and time goes slower and slower the closer you're to the center. In the end, the light cone crosses the boundary of the black hole, the so-called event horizon. At this point, it gets so distorted that now it's literally pointing downwards. We can say that time has changed its direction. Time is pointing downwards. What kind of nonsense is that, you may ask? It'll be easier to explain in a real example. Imagine you're a crazy astronaut who decided to jump into a black hole, and there's an observer in the spaceship who watches you doing this for some reason. At first, for you, nothing changes. You look at your watch, you see that 5 minutes have passed, and everything's okay. But for the observer, first of all, you'll fall for a very long time. The observer has been sitting there for 50 years, and you're still falling, all because your time has slowed down. Secondly, since space is also distorted near the black hole, the observer will see how you'll begin to stretch like spaghetti. This is a scientific term, by the way. It's called spaghettification. And then you finally cross the event horizon. The observer doesn't see you anymore. Light cannot escape from a black hole, so your image won't reach the observer even if you're still inside. And what about you? What if you somehow survived? Remember, the time arrow is pointing to the center of the black hole. What does it mean? It means that now, the center of the black hole is your future. It isn't a place, it's a fate that you can't change. And wherever you came from, as well as the rest of the universe, no longer exists for you. Because now, it's not a place, but an event from the past. And since you can't turn back time, you'll never be able to come back. But what is around you? Complete chaos. The rays of light now move in all directions, forward, backward, and so on. The rays depicting the events of the past, the future, the present, all this is moving around you. In reality, space and time didn't swap places, but it feels like they did. Because in space, you can now only move forward, as if along a straight line. And time, reflected in the light rays, surrounds you everywhere and moves in all possible directions. And here we go back to the beginning. This horrifying example helps us imagine what it would feel like if time and space got reversed. Of course, all this is just theories and guesses. The very idea that we're moving in some one direction, the one we haven't chosen, and there's complete time chaos around, sounds quite frightening. And yet, it would be a very interesting experience. Sounds dangerous. Why don't you go first?
We've never sneaked a peek beyond the edge of the observable universe. What lies there? If we managed to get there, would we find another universe? What if the universe we live in is just one of billions of trillions of other universes? I'm talking about the concept of a multiverse now. Look, there's this idea of parallel universes. Let's take one of them. It looks exactly the same as our universe, and still, some details differ. Maybe instead of becoming a doctor, you chose to start a music band there. Maybe one infamous asteroid changed its trajectory, and dinos are still roaming Earth in that universe. But the multiverse theory takes it all one step further. Those who believe in it state that there might be countless realities. According to this theory, we live in a bubble that is just one of many other bubbles, which I guess looks like bath foam. These bubbles constantly bob up and vanish. Multiverses are described by a few scientific theories, which mention various possible scenarios, from separate universes that keep springing into existence all the time, to regions of space that are in different planes than our home universe. But there's one thing these theories agree upon. All of them suggest that the space and time we observe is not the only reality. You see, it's impossible to explain all the quirks of our universe if it's the only one to exist. So it's either inventing newer theories that can throw light on certain properties of our universe, or accepting the fact that we're living in just one of many, many universes, all of which are different. One of the most widely known multiverse theories is called inflationary cosmology. This is the idea that right after the Big Bang, the universe expanded rapidly and exponentially. Indeed, cosmic inflation does explain lots of the properties of the universe we observe, for example, the distribution of galaxies. When this theory was suggested for the first time, it was perceived as a piece of science fiction, but it can indeed explain tons of interesting features of the world we live in. So with time, people started taking it seriously. Now, the theory states that inflation might happen again and again, maybe even infinitely, and this could create constellations of bubble universes. Of course, none of these bubbles will have the same properties as ours. There may easily be places where physics as we know it doesn't exist. But even though some of these universes might look like ours, they all lie beyond the realm we can observe directly. Another theory, called the many worlds interpretation, claims that there might be multiple branching timelines, or alternative realities. And in each of those realities, our decisions play out differently, which also means very different outcomes. At the same time, the only reality you can perceive is the one where you live. If it's true, then the question is, where are all those other universes? Well, they most likely all overlap in dimensions we absolutely can't access. And at the moment, it's not possible to travel between universes. But who knows? Maybe a few thousand years later, people will not only find a way to prove that parallel universes exist, but also invent a method to hop from one of them to another. Unfortunately, so far, there's no solid evidence that multiverses exist. All the proof we've got today is purely theoretical. Some experts even argue that it could be an unbelievable cosmic coincidence that the Big Bang created such a perfectly balanced universe as ours. Or, if parallel universes do exist, we might have just inhabited the one that had all the right conditions for our survival. It's still unclear whether the multiverse theory is even testable. Perhaps we just haven't thought of the right tests yet. Now, I've got one scary thought for you to consider. What if, at one point, you stopped existing in your home universe, the one you were born into? What if your consciousness was transported to a parallel universe, where you're now watching this video? Think of this.
You know how Stephen Hawking said, the best evidence we have that time travel is not possible and never will be, is that we have not been invaded by hordes of tourists from the future. But what if these tourists come to our time, but they do it secretly? You may even have met one of them. Let's see the most famous time travelers. Meet Orin. He's a cyborg who came to us from the year 2050 to stop the coming end of the world. In 2020, he appeared on a TV show where he said the whole world was inside the Matrix. Then he hit the headlines and gave an interview to a popular YouTube channel. As proof that he's a cyborg, he demonstrated his robotic voice, which can be made in a simple computer program. He also called himself We because he declared himself a collective consciousness that had come to save humanity. Orin became famous for his predictions about the near future, but it turned out that many experts had already announced these forecasts earlier. He also said that a huge corporation was suppressing humanity, and we were inside a complex computer simulation. If we don't improve or care for each other and nature, the end will begin in 2050. Orin no longer appears on major shows, but he has a small fan base of people who love all sorts of fantastic theories. Another time traveler is Adam Archin, who came to us from 2045. There was an interview with him on YouTube where he shared some details about the future of the US, after which the video went viral and hit the lines in many newspapers. Archin reported that the last official president of the country would be the daughter of Martin Luther King III, and she would become the greatest US president in history. Another exciting event that Archin announced is supposed to happen in 2028. He said that people would learn about the existence of extraterrestrial civilizations. He added that these creatures wouldn't come from outer space. The traveler also noted that the world would switch to a single digital currency and all cash would disappear. Of course, no one believed him, so the experts conducted a lie detector test. And Adam Archin successfully passed it. He said that he had a chip in his hand to facilitate time travel. An extraterrestrial civilization would arrive on Earth in 2028, and in 2045, people would be closer to robots. The lie detector didn't state that Archin was lying, but this doesn't mean he told the truth, since the device can be deceived with the help of special training. In any case, in 2028, we will find out whether Archin was right or not. All these time travelers arrive in the past and, for some reason, don't use knowledge from the future. What would you do if you could go back 50 years? Perhaps you would invest money in shares of some young company that will become a big, expensive corporation. In that case, everyone would believe that you really came from the past. And by the way, one guy did it. He invested $800 in the stock exchange and made $350 million out of it. This guy's name was Andrew Carlson, and he hit a big jackpot in 2003. However, he didn't manage to enjoy a rich life because the FBI came for him. Andrew sold some stocks and bought others, and did this very successfully. Thus, in a few months, he became a millionaire. The Securities Commission couldn't believe in such coincidences, so it called the FBI. During the interrogation, everyone was sure Andrew would begin to justify himself and say he was lucky. But instead, he calmly replied that he came from the year 2256 with the help of a time machine. Of course, no one took it seriously. But when the FBI started looking for information about this man, they found nothing. Andrew Carlson had no documents. He was not in any database. He just appeared out of nowhere and started making a lot of money. He was interrogated for about 4 hours, and he behaved pretty calmly. It seemed as if he was telling the truth. However, he didn't tell them the time machine's location. When the press found out about this man, he immediately became a celebrity. Well-known news sites began to write about Andrew Carlson. Articles have appeared in Japan, Australia, Germany, the UK, and other countries. And of course, journalists started calling the FBI to find out more details about this guy. And the FBI told them that the whole story was fiction and that there was no Andrew Carlson. Information about him appeared on an internet resource known for its fake news. At some point, the article about the time traveler somehow got into Yahoo, where it went viral. So, as we see, all statements about time travelers are either fiction or a lie. Conversations about such travels appeared thanks to fantastic films and books. Pop culture has greatly influenced this fantastic concept and created several theories claiming that time travel is real. And some people believe that, especially those who are far from science. But what do real scientists think about this? Are such trips really possible? Let's try to find out. Scientists say yes, time travel is real because we're now traveling in time. Time is moving forward and we're moving with it. We call it a journey. But if we need to get into the future or go back to the past, everything is much more complicated here. Remember Einstein's little theory of relativity? It says that time moves relative to the observer and has no constant value. To understand better, here's a simple example. 10 hairs on your head. Is it a lot or a little? 10 hairs in a bowl of soup. Is that a lot or a little? Everything is relative and depends on the conditions. The same thing happens with time and space. If we move at a tremendous speed, close to the speed of light, then time slows down for us. The perception of time becomes different for a person who's running and for one who's standing still. If we're near some heavy object, let's say 1,000 times heavier than the sun, then the time next to this object also slows down, thanks to its strong gravity. In this sense, time travel is possible. If you're an old person and meet your friend as young as he was 50 years ago, Why are you so young? Oh, I've been flying in space at a tremendous speed all this time, that's all. But this doesn't mean that this friend just sat on the ship for 50 years and didn't age. No, time was different for him. 10 years for you on Earth is a long period of time, but for him, these 10 years passed like half an hour. Gravity and speed bend time. For this reason, astronaut Scott Kelly, who spent a year and a half in orbit, became 5 milliseconds younger than his twin brother after coming to Earth. All this time Scott spent inside the ship flying in orbit at high speed, and he was also further away from the gravitational center of the planet. So, time was slower for him by 5 milliseconds than for his brother. Objectively, time always runs at the same speed, but its speed changes inside the perceptions of different observers under different conditions. That's what the theory of relativity is about. But what about jumping into the future or the past, like in movies? Wormholes will help you with this. This is something like tunnels that pass through space and time and can connect different time segments in different places in the universe. They are like cheat codes that can break the laws of the universe. Wormholes are elusive, have different sizes, are unpredictable, appear in space, and vanish. But their main problem is that wormholes only exist in theory and sci-fi and have never been noticed in our universe by scientists.
Have you heard of quantum immortality? These days, many people are confused about this notion. But if you believe in it, you also believe that you can live forever. How come? Well, quantum immortality claims that nobody ever disappears forever, and that consciousness never passes away. Instead, once you cease to exist in one universe, your consciousness simply gets transferred to a parallel universe, and there, you survive. This idea sounds more like a sci-fi movie than something that real science can suggest. It could be a script for a blockbuster. People's consciousness can transfer from one world, where an apocalyptic event has wiped out all life, to another, where such an event has never occurred. And the only clues about the slight differences between these worlds are a few Mandela effects. This phenomenon is named after people disremembering Nelson Mandela's passing. These days, the term is used to refer to any collective false memories. So maybe in that new world, millions of people will be wondering, since when has Pizza Hut been written with 2 T's? But the thing is, in this new reality, this popular brand name has always had 2 of them. Imagine going through apocalypse after apocalypse, transferring to one world after another. It might be a nice, if a bit horrifying, thought that you're going to live forever. Instead of passing away completely, you'll just keep transferring to a universe where nothing tragic has happened to you. But is there anything to this theory? What does science think about such a possibility? In fact, the idea of quantum immortality has been around for quite some time. It has been seen both as untestable nonsense and as a curious thought experiment, like the one involving a cat. And here, I mean Schrödinger's cat. Let me explain. According to one of the interpretations of quantum mechanics, particles can exist in several states at the same time. But when a particle is being observed or measured, this system collapses. As a result, the particle is found in just one of its possible states. In 1933, Schrödinger suggested doing a certain thought experiment. He believed it would show the absurdity of this idea. In his hypothetical scenario, a cat was placed inside a box with radioactive materials. These substances had a 50-50 chance of decaying over an hour. If it happened, the radioactivity would be detected by a Geiger counter, which, in this case, would smash a vial with poison. As you might assume, it wouldn't end well for the cat. Schrödinger saw the following problem. The cat in the box would be both alive and not alive at the same time. The animal would be in this state for an hour, until someone opened the box and checked on the feline, either lifeless or very annoyed. One solution to this problem, known as the many worlds interpretation, gets around this situation by claiming that both outcomes take place. According to this hypothesis, all possible outcomes of quantum measurements occur across many universes, and their number might be infinite. It probably doesn't come as a surprise that this theory is often criticized. Many mention that this idea is unfalsifiable since universes don't interact with one another, making the theory impossible to test. It's even been called one of the most implausible and unrealistic ideas ever. After all, it's not clear why your consciousness would get transferred between worlds just because you cease to exist in one of them. Unless it's a thought experiment, of course. It might provide you with the comfort of knowing that there is another you who doesn't pass away in a different world. But why should you believe that you only exist in the world where you're alive? What about the universe where you didn't make it? Like, what happens to your body? And speaking of the suggestion that you might understand that you're in a different universe thanks to Mandela effects, it's kind of the area of science fiction.
So, you're standing on a diving board in the middle of an open space. You look down, but that's not a pool. It's a giant black hole. Well, what the heck? You start swinging and then you jump. The gravity of the black hole grabs you, and you pick up speed. Just a little more, and you'll enter the dark abyss. But you're not afraid. You're sure you can survive the fall into the black hole. Besides, you have a clear goal to travel through time. But first, let's figure out how it works and why time stops near a black hole. This is the space-time grid. It's what our entire universe is made of. And just like a regular grid, it sags if you put something heavy on it, like me. For example, let's put the planet Earth here. You see a little funnel that is formed around the Earth. And if you put a small ball next to the planet, it'll roll into the funnel. That's how gravity works. The heavier the object, the more it bends space-time. By comparison, here's the Sun. It's almost 333,000 times heavier than the Earth, so it makes a really big funnel. So big that all the planets in our solar system move around that star inside that funnel. So now, let's put a black hole on a space-time grid. Its centers are infinitely heavy, so they create a limitless deep well. And anything caught in the black hole's gravitational field can never leave it, not even moving at the speed of light. Okay, their gravity is infinitely strong, but why do they slow down time? It's all about the speed of light. According to physics law, the speed of light must be the same at every point in our universe, even in a black hole. So, for our experiment, we take this ball, a photon of light that can travel 671 million miles per hour. You could get from Earth to the Sun at that speed in 8 minutes. That's how long it takes light to travel from our star to our eyes. So, when you're looking at the Sun, you're looking back in time 8 minutes ago. By the way, don't look at it directly. Now, the critical thing to remember here is that velocity consists of two physical quantities: space, miles, and time, hours. We'll use that later. Now, let's look at the black hole in our space-time grid. In three-dimensional space, it appears like this. But if we assume that space is two-dimensional, our grid looks like this when viewed from above. Just a lot of squares. And this is the black hole right in the middle. If you look at the grid from the side, you'll see a straight line. And the black hole here looks like a pit, or like an endless well. Now, let's follow our photon of light in three-dimensional space. Here, it's moving toward the black hole, and then it falls into the well of the black hole, and it continues its motion at a constant speed. Now, the side view. Again, the photon moves from left to right and then falls. Its velocity doesn't change. The problems begin if you look at the experiment from above. When the photon of light moves in the distance of the black hole, its speed is stable. But then it goes down into the well. First, it slows down and then it just stands still. But it's moving downwards. The photon moves in an arc down the well in the lower dimension without changing its speed. But in the higher dimension, it traveled a minimal distance at the same speed. Usually, this would mean that the photon was moving at a low speed in the second case, but not in the case of the speed of light. Remember, it must be the same at every point in the universe. The number 671 million miles per hour shouldn't change. So, we change the very parameters of that number, time. Time itself must slow down so much that this slight movement of the photon, when you look at it from above, was at the same speed, 671 million miles per hour. But if you go down and look at this well much lower, you see that its walls are almost vertical. So, a photon of light would be moving in a vertical trajectory. That means that if you look at it from above, the photon will just be standing still. Again, its velocity can't change, so time will vary. At that point, it should just stop. This is what happens near a black hole. Now, if you look at a black hole, you can see this effect in action. It swallows up the light around it. But as for an observer, it seems to you that the light stays in orbit around the black disk. In fact, at that moment, the photons are still moving at the speed of light inside the black hole. It's because time has slowed down there so much that you feel like the light has stopped there. This disk is called the event horizon, the point of no return, the last stop before you go into the black abyss. And at the very center of the black hole is the singularity. This point of space is so dense that if you tried to describe it with any numbers or physical quantities, they would all tend toward infinity. Simply put, all the laws of physics we know just stop working here. So scientists can't say exactly what awaits you in the singularity. Before you make that jump into the black hole, let's drop a space probe there with a blue light that flashes once per second, and let's attach giant clocks to it. You see the probe falling into the black hole, gaining speed. But then it starts to slow down. Moreover, the probe flattens out and seems to spread out around the black hole. And then you notice that the blue beacon on the probe has changed its light. It now flashes as red. It's because the light is a wave. Blue is a truly short wave with a high frequency. But the black hole's gravity acts on this wave, stretching it out. The light waves get lengthened and become broader and less frequent. The new wavelength and frequency match with the red color. It's called redshift. Also, the probe blinks now not once a second in short beeps, but lights up and goes out for a long time. It's because of the time warp. If you, as an observer, look at the clock on the probe, the second hand there barely moves. However, the clock on your hand works as usual. But if you could be in a black hole, time would seem normal to you, and the arrow on the clock would move as it did before. But the hands on the clock outside the black hole would move like crazy to you. That's because time goes much faster outside the black hole. Oops! Your probe just got ripped apart. That's because of the substantial difference in gravity that acts on the probe. The black hole's gravitational force increases with every foot of approach. That is, if you were to extend your hand toward the black hole hard, the gravity on your fingers would be much stronger than on your shoulder. This force would cause your fingers to lengthen, simply like spaghetti. That's why many people think it's impossible to survive falling into a black hole. But scientists think you could survive without a problem. Hey, maybe they should jump first just to make sure. The thing is, you have to pick a black hole as big as possible, like the ones at the centers of galaxies, for example. That bright spot at the center of the Milky Way also has a black hole. It's about 1 million times heavier than the Sun. And this is the Messier 87 galaxy, one of the most massive galaxies among our neighbors. In 2019, humanity got its first ever photo of the black hole at the center of this galaxy. It's about 6.5 billion times heavier than our Sun. So, it's the perfect place to make your jump into a black hole finally. Let's go. At first, you feel a strong acceleration as the incredible force of gravity grabs you. But in the case of a supermassive black hole like this, the gravity doesn't change as dramatically. That's because of its size. Right now, the gravitational force on your legs is about equal to the gravitational force on your head, so you don't turn into spaghetti, and you feel comfortable. You see that the light from the stars and all the space around you has begun to shrink at a certain point. It means that you have already passed the event horizon and are now moving toward the black hole's heart. As a result, the light of the universe becomes a small dot for you and then disappears altogether. If we look at our space-time grid, you're already falling into a well. Time is completely stopped for you. However, the rest of the world continues to move steadily through time. If you could now look at the Earth from a black hole, you would see a time lapse, an accelerated video of how the months and years go by on our planet. If you had a jetpack that had an incredible engine to pull you out of the black hole, then you can make a jump forward in time. In 1 second, centuries on Earth could pass in the heart of a supermassive black hole. But this only works one way. You can't go back in time. But for now, you keep falling into the black hole. Beyond that, no one knows what'll happen to you. We only have theories about wormholes and white holes that might transfer you somewhere else in the universe. So, enjoy your trip, and just think about all the frequent flyer miles you're racking up. Oh boy, you can't stop seeing images of funny pandas on your final exam sheet. All those late-night YouTube videos hit you hard, huh? You scribble down some words, hoping that something makes sense. You look at your watch and realize you've got only 10 minutes to finish. Panic mode is officially on, but no one knows your watch has a pinch of magic in it. You click the stop button on your watch and relax. Don't worry, no one will turn to dust and half the universe won't disappear. You simply freeze everything in time except yourself. With this ability, you can stop the time for 1 minute a day. So after freezing time, you get to one of your classmates, take a picture of the assignment, and head back to your seat. You unfreeze the time and write down the proper answer. Whew! At least you can guarantee a passing grade. I'm Steve from Legal. Want to make sure you know that Brightside does not condone cheating on a test. Okay, carry on. You walk out of the classroom with a large smile on your face. You check your watch and it says you spent 10 seconds of time freezing. 50 seconds left. After that exam, you go and grab something to eat. You're at the traffic light waiting to cross the street. Hey, there's a girl talking on the phone and a car is speeding up to her. Everyone sees it, but nobody can do anything, and the car is only a few feet away from her. You click the stop button and everything freezes again. You run up to that girl and move her as fast as you can. Then you run back to where you were standing and click the button again to unfreeze time. Everyone is confused, but at least the girl's safe now. The whole mission took you another 10 seconds. 40 seconds left. You enter the coffee shop to grab a quick bite. As soon as you get your coffee, you turn around and lose balance. Your drink is falling down and about to spill. You click the button instinctively, and the drink is now literally hanging in the air. You collect all the droplets and put them back in the cup and click the button again. You just saved yourself $5 and a dry cleaner's trip. You realize you spent 15 seconds saving your drink. 25 seconds left for today. As you're walking to the bin to throw away the cup, someone bumps into you. The buckle unfastens and the watch smashes onto the ground. You pick it up and see a scratch on the display, plus some parts came off. You gather the parts, trying to fix it. As you're doing so, you see a fly next to you and shoo it off. Strangely, it doesn't even flinch. You look around and see everyone frozen in time. The person who bumped into you is still in mid-motion. The pigeons eating breadcrumbs are frozen too. So are the cars and people. Since the watch got damaged, it reversed the power. Everything is on pause, and now you've only got 25 seconds of regular time. If you waste it all, you'll be frozen in time forever. At first, you try your best to fix it, but don't know what to do. You take out your phone to browse some tutorial on how to fix a watch, but it won't load. You keep refreshing, but nothing happens. The internet can only work in real time, and 25 seconds aren't enough for anything. There's only one place now where you can learn how to fix watches in this situation: a library. You'll have to read about it and learn from scratch. You rush to the closest library, which is at the campus. Turns out there are only a few books on how to repair watches, but they have zero info you need. You find a bike and pedal all the way across to the public library. It took you 4 hours to get there. Once you've arrived, you look at endless bookshelves. You could easily switch back to real time and ask the librarian where to find what you need, but then it might take longer than you have left. There are way more books than you expected. You pedal back home and grab some stuff to sleep and eat. It's gonna be a long day. When you're back, you grab a few large books that seem to have the answer. No social media can distract you, since the internet doesn't even work. The time passed and you finally finished 2 large mechanics volumes. But there's just one problem. You can't find volume 3. Your only chance is to turn on time to do a quick internet search on where it is. You can't download an ebook since it will take much time and it's impossible to print in frozen time. You click the button and time resumes. Everyone looks confused about a mattress and food leftovers all over the library floor. But you do a quick internet search and find out that you can order the book now and receive it the next day. Yeah, right. It turns out the closest book is in a library on the West Coast. Bad news, you're in New York. And what makes it worse is that the only source was updated years ago. The book may not even be there. You freeze time again. It took you 10 seconds to get all the needed information. You have no choice but to go on a road trip that will take around half a year by bike. No other vehicle is available to you. You find the best bike and gear, pack up some provisions, and leave the town. You travel through the mountains, swamps, and dry lands. You bike through frozen waterfalls and cut across heavy storms, frozen in time. You find indoor places to sleep, since time is frozen during the day. But you actually took your time getting there and lengthened your trip to see all the sights around the country. You spent a week at the Grand Canyon and a month in Yellowstone. You went up to bears and wolves so you can actually see the details of their muzzles. You even decided to pedal all the way to Mexico to check out the amazing scenes and landscapes around. You visited all the cities and towns without worrying about money or a proper place to stay. Steve from Legal again. Brightside does not condone using stuff without paying for it. Remember, this is a fantasy trip. Okay, continue. After covering all of Mexico, you continue all the way down through Central America, where you got to witness even more amazing sights and landmarks. Hey, you've already gone this far, why not continue pedaling down to South America? You can even visit your friend in Argentina. I mean, he wouldn't know you're there, but it would be nice to pay him a little visit. After sunbathing in Brazil and mountain climbing in Bolivia, you end up at the southernmost point in South America and admire the journey you took. Right across the ocean is Antarctica. It's impossible to get a boat and sail there, so you decide it's time to get back to business. According to your calculations, it took you about 4 years to complete this journey. But you finally reach the library. You take out some water to drink, but accidentally drop the watch on the ground and resume time. Everyone is in motion. Cars are honking their horns, dogs are barking, people are screaming and shouting at each other. You haven't heard a human voice in such a long time. Some people are staring at you. You're overwhelmed by all the energy around you, but suddenly wake up from it. You fumble trying to find the watch. Here it is. You stop the time. Only 3 seconds left. You spend what seems to be another month in that large library trying to find the third volume. You've got no more time to do another internet search with those 3 seconds. After you finally found it, you spend 2 more months figuring out how to fix your watch. When you're done, all you have to do is click the button to bring everything back to normal. But you decide to pedal all the way back home. You clean up all the mess in the library and go back to the coffee shop where it all started. You even return the bike you borrowed. This is it. 3 seconds to see if all that work was for nothing. You click the button and watch time move on. You look at your watch. 3, 2, 1. Whew! Everything is back to normal. You go back home and lock up that watch in your drawer, never to look at it again. Until next time. Hi, you know what I'm thinking? Of course you don't. But I'm thinking someday someone will finally invent a time machine and you'll be able to travel back and forth between the future and the past. But the good news is, you already have the superpower of slowing down and speeding up time right now. The older you get, the faster time seems to fly by. First of all, the way you perceive the flow of time depends on how much information you absorb. When you were little, everything was new to you. Your first bite of pizza, your first trip to the ocean, the first time you saw a giraffe. Yeah, that was cool. All of that took a lot of brain power to process. Your brain was recording every new detail in your memory, and it seemed like it took more time. The older you get, the more neural connections your brain has. It's like a tree with many branches. Your tree keeps growing, and it takes less time to process the same amount of information. You also learn how to feel the passage of time more accurately. There's also a mathematical explanation. When you're 10, 1 year is a whopping 10% of your life. I mean, waiting a whole month more for your birthday presents feels like an eternity. When you're 20, 1 year's only 5% of your life. As you age, 1 year more or less keeps becoming less and less significant. That's why the 5 years between the age of 5 and 10 can feel as long as the 40 years between 40 and 80. Your biological clock never stops ticking. Your metabolism, heartbeat, they all slow down over time. You take less breaths and have less heartbeats per minute, and you feel like time's speeding past. Hey, I know that feeling. You can try to fool time a bit and play the vacation paradox card. There are two different ways to perceive one event: when it's still going on and after it's already ended. When you're on vacation, discovering and seeing new things, time seems to fly by. When you come back home, it feels like it's been forever, even though you were only gone a week. So, if you try new things every day, meet new people, or constantly learn new skills, you'll speed up the passage of time but stretch it out in your memory. To boost the time-slowing effect, you can spend a half an hour before bed remembering what you did that day. You'll be more engaged in the moment, and even regular daily things will feel more unique and new. When you have to stay home for a long period of time and don't have a schedule to keep, time seems endless, and the future never seems to come at all. About half of us think the future's moving towards us. The other half believe they're going forward, and the future is something stuck and still, like you're a train and the future is your final destination. To find out which group you're in, take a go at solving this little riddle. A party planned for next Friday has been moved forward 2 days. When is the party going to happen? If you said Wednesday, you believe you're still and the future is moving. If your answer is Sunday, you think you're moving towards the future. When you're waiting for something to happen or just feel bored because you have nothing to do, your mind starts wandering. You start to oversense your own bodily feelings, and time seems to expand. Hunger also affects your perception of time. Scientists tried showing pictures of desserts to hungry and full participants. Those who were full didn't have the motivation to make time rush by. They felt like they were shown the pictures for longer than they actually were. Another experiment proved that nature can also make time go slower for you. Participants who went for a walk through the wild felt like it lasted longer than the same walk in the city. Even watching videos of awe-inspiring natural objects like waterfalls gives the illusion that time has frozen in place. When you're doing something you enjoy, your mind is focused on what you're doing. You don't have time to track time. It works even better if you're trying to achieve a goal. All that excitement makes you feel like time flies. Sometimes, it can get you really stressed when you can't figure out where all that time's gone. If that happens to you at the office, just leave your cubicle or the entire building for at least 5 minutes. It'll help put you right back on track. You get to see some events in your life, especially scary or sad ones, in slow motion. That's because of how your memory works. When you're living through a fearful moment, your brain activates one of its superpowers, noticing and analyzing every single detail. That's why people who get in sticky situations often feel like time just froze. They say that's what gave them time to react properly and get out of any danger. You probably inherited this talent from your ancestors. They needed the ability to slow down time just to survive their day-to-day lives, and that saber-toothed tiger over there. Some emotions can speed up your internal clock, others slow it down. Uncertainty has the power to stretch time. When you're waiting for test results, 10 minutes can feel like an hour. Your brain goes into overdrive, paying attention to every insignificant detail. When you're doing something routine, time goes by faster. You don't usually feel strong emotions, and you just end up losing yourself in your own thoughts. When you're doing something unique, like performing on stage, you get fully self-aware and focus hard on every moment. That's why time seems to freeze. When you're given a deadline, no matter how distant, you can't be fully present in the moment. Your mind gets obsessed with finishing the task, and doesn't notice the small details, like if you're getting hungry, thirsty, or tired. Distractions are key to stopping time from running away from you. If you look at the clock too much, you can experience something known as the stopped clock illusion. When you're busy with something and glance over at one of those old-fashioned clocks, the second hand seems to freeze. Then, time sort of restarts and goes on. This happens because when you move your eyes quickly from one object to another, there's a quick break in your vision. When that happens, it takes you off autopilot, you get confused, and your sense of time gets all wonky. To feel it, stretch your arms out in front of you and quickly shift your eyes from one index finger to the other. When you do it, you'll notice a tiny moment of, well, nothing. Your brain tries to always give you a seamless picture of what's going on around you, and when your eyes move so fast, there's a pause in input that has to be filled with something. Your body's internal clock is actually kind of perfect. How often have you woken up a few seconds before your alarm? The sciencey word for it is circadian rhythm, and it dictates when you're active and when you have to go to bed. It's regulated by a special protein. It loves and needs routine to function well. If you go to bed and wake up at the same time every day, the protein will adjust your body to your new schedule. When you have to wake up super early just once, say you have a flight to catch, you worry a lot about it the night before. Your body knows what time you set the alarm for, and it ramps up your stress level about an hour before you actually have to get up. When you hit the snooze button, you're basically throwing away all the work your body did to wake you up. Your internal clock starts spinning in the opposite direction, your hormones go crazy, and you feel sleepier than ever. The more times you hit snooze, the worse it gets. The easiest possible way to travel in time is to take the elevator to the top floor of a skyscraper. Time runs faster up there because gravity gets weaker with every floor. Now, before you get too excited, we're only talking about a few fractions of a nanosecond. You could try moving to some distant planet if you wanted to live longer, but that wouldn't make a huge difference either. You might live to be 200 Mercury years old, but no one would be around to throw you a birthday party.
Even though it may seem that science has reached the level where there are no more mysteries left, it's not exactly true. And no modern physicist would dare to assume that our knowledge of the universe is near completion. What are scientists still wondering about? Let's figure it out. For one thing, dark energy keeps puzzling researchers even today, because the universe doesn't seem to add up. Even though gravity is pulling space-time, the very fabric of the cosmos, inward, the universe keeps expanding outward, and this process is speeding up. That's how the concept of dark matter was born. It's believed to be some invisible agent that counteracts gravity by pushing space-time apart. It goes like this. The universe expands, and more space appears out there, and with it, more dark energy. According to astronomers, this invisible energy must make up more than 70% of the universe. But no one knows how or where to look for it. Then there's dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Scientists call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. Its existence is inferred from the effects it has on visible matter, radiation, and the very structure of the universe. There are a few special detectors on the lookout for weakly interacting massive particles, of which dark matter might be composed. But so far, nothing has been found. One of the most recent studies claims that dark matter might produce long, fine-grained streams radiating out from Earth like hairs and streaming throughout the universe. But it hasn't been proven yet. Then, there's the question of antimatter. It's the oppositely charged and oppositely spinning twin of good old matter. The intrigue here is why there is more matter than antimatter in our universe. It would be logical to assume that the universe would want to treat matter and antimatter equally. Thus, at the moment of the Big Bang, equal amounts of matter and antimatter should have been produced, right? Not really. If it had happened, there would have been a moment of total annihilation. Protons would have canceled antiprotons, electrons, anti-electrons, and so on. It would leave behind a lifeless, matterless expanse of space. Luckily, for some mysterious reason, when the universe was created, there was some excess matter. It didn't get annihilated. and that's how everything started. But there's still no accepted explanation for this. Then, we've got particle physics questions. They account for many unsolved problems. Sonoluminescence is one of them. Let me explain. Let's say you take some water and hit it with sound waves. It forms bubbles, low-pressure regions surrounded by high pressure. Once the outer pressure pushes on the lower pressure air, the bubbles collapse. But while collapsing, they emit light, even though the flashes don't last for more than a trillionth of a second. What bothers scientists is that it's unclear what the source of this light is. There are a few theories, of course. Some experts think tiny nuclear fusion reactions might be involved in the process. Others believe some kind of electrical discharge comes into play here. There's also the idea of compression heating of the gases inside the bubbles. None of these theories have been accepted yet. This might sound surprising, but we haven't figured out what exactly gravity is either. Other forces are mediated by particles, but not gravity. Some physical theories claim that it might be carried by a hypothetical massless particle called a graviton, but no one has seen these gravitons yet. We don't even know what kind of detector can be built to spot them. Even if gravitons come into contact with matter, and we aren't sure about it, they do it extremely rarely. There's also a theory that gravitons are closed loops of energy, but again, it's just a theory so far. There are tons of other unanswered questions bothering our minds. What happens inside a black hole? Is string theory correct? What is the fate of our universe? Do we live in a false vacuum? Hopefully one day we'll find the answers to all these mysteries. With each passing day, we learn more and more about the world around us. But some of the most fundamental questions that have been bothering humankind for centuries remain unanswered. For example, where does the universe end? Or even better, can it be infinite? We know that our universe is around 13.8 billion years old. That's quite a lot, but it may be even older. You see, some parts of the universe can be too far away for the light from those mysterious regions to have reached us. That's why we have the notion of an observable universe, which is the parts of the universe we can actually see. What happens beyond is unclear, and we might never find out the truth. But the question of whether the universe is finite or boundless depends on its geometry. The general theory of relativity allows three possible shapes for the universe: open, closed, or flat. The open one resembles a saddle, the closed one looks like a sphere, and the flat one can be compared to a sheet of paper. After performing complex calculations and observations, astronomers are almost certain that our universe is flat, and this might mean that it is infinite. On the other hand, it could simply mean that the universe's geometry is so complicated we can't perceive it. There are also other studies that suggest that the universe might be closed, therefore, it's probably finite. Unfortunately, we're unlikely to find out the truth anytime soon. Now, if the universe was finite, could it have an edge? Since its formation all those billions of years ago, the universe has never stopped expanding. So, now, the regions of space at the edge of the observable universe are way farther away from us than when they emitted the first light. It means the edge of the observable universe is around 46 billion light-years away in every direction. Imagine a sphere with a diameter of 92 billion light-years and a volume of 410 nonillions, which is 410,000 billion cubic light-years. Here you go. It's our observable universe. But no one knows whether these ginormous numbers are the real limit of the universe, with nothing beyond. It would actually be very arrogant to claim that. The chances are there's a whole different world beyond the edge of the observable universe. But even if the universe is finite, it might still not have an edge, like our planet. It's obviously finite, but have you ever seen its edge? Unlikely. So everything depends on the geometry of the universe. Okay, if the universe is infinite, it indeed can keep expanding without getting bigger, since you can't get bigger than infinity. When the universe expands, space itself inflates, which creates additional distance between objects. And astronomers are sure that it happens no matter whether the universe is infinite or not. Now the next question is what the universe is made of. Everything we can see around and in space with the help of telescopes and other instruments is known as normal matter. It's made up of atoms and molecules and adds up to less than 5% of the universe. Around 27% of the universe is dark matter, and almost 3/4 of the universe is dark energy. Astronomers wouldn't even know the thing existed if, some time ago, they hadn't found out that, instead of slowing down, the expansion of the universe was accelerating. It means there is some enigmatic force counteracting gravity. It got the name of dark energy. At the moment, we have no idea what dark matter and dark energy are. As for the 4.9% we do understand, about 74% is hydrogen, 24% is helium, and the rest is heavy elements. Another intriguing question is whether the laws of physics are the same everywhere in the universe. Well, there's no convincing reason why it should be the case, but when scientists tried to measure tiny differences in the constants ruling the forces of nature, it turned out that these laws were the same everywhere and at all times. At the same time, some studies have shown that one constant determining how electric charges interact might have been different in the past. But most researchers agree that this finding is controversial and currently unproven.
What is the fastest moving thing in the universe? That we know about, of course? It's light. Its speed in a vacuum reaches 186,000 miles per second. If people could travel at such insane speeds, we would have already explored hundreds of new worlds which are inaccessible to us today because of how far they are located. Interestingly, while traveling at the speed of light, you would experience time differently. Your mass would become infinite, and you would slow down. That's because the faster an object moves, the more mass it has. That's why, in real life, traveling at the speed of light in the conventional way doesn't seem possible. Okay, another question. Could we slow down the speed of light? In 2015, a team of scientists from Scotland claimed they had found a way to do just that. They sent protons through a special mask, altering their shape. And in this malformed state, super tiny particles of light started traveling way more slowly than regular protons. It's true that the difference in speed was almost imperceptible, but the fact they had managed to do it was amazing. It means that the speed limit of light isn't as unchangeable as we thought before. It's another question why anyone would want to slow down light as if it's not slow enough as it is. Ah, I see. This last statement might sound confusing, but let me explain. We humans are used to traveling at unhurried speeds of 60, 70 miles per hour on the highway. So to us, the speed of light seems to be unreachable. But how about this? If we reduce the observable universe to the size of our planet, crossing the Milky Way galaxy would be like walking a few houses down the block to visit your friend. And still, it would take a whopping 100,000 years if you traveled at the speed limit of this Earth-sized universe. This example shows how incredibly slow it would be for a spaceship to explore other worlds at the speed of light. Crossing our home galaxy would span more than 100 human generations. And even if we let humans be and concentrate on protons dashing across the solar system, the speed of light would still turn out to be too sluggish. Astronomers have calculated that it takes light almost as much as 45 minutes to travel the distance between the Sun and Jupiter. And it takes light 5 hours to reach Pluto. When you look up at the sky at night, you see stars as they were a long, long time ago in the past, thousands of years. That's how long it takes the light they emit to reach us. So now that we know that the speed of light is indeed pretty slow, we can try to find the answer to the main question. Why is it so? So far, the only answer astronomers have is because. A tiny bit more satisfying version of this answer sounds like this. The universe is designed in such a way that protons move with such velocity. There's no specific reason why it should be this way, it's just the way it is. As you see, the answer is a non-answer at the same time, and we're simply stuck in this slow universe. But would it be better if light was much faster? What would our lives look like if the speed of light was boosted by a factor of 1,000? Then, a spaceship moving at the speed of light could cross the Milky Way in less than a century. A trip to Alpha Centauri, the closest star to Earth other than the Sun, where potentially habitable planets may dwell, would take less than 2 days. Computers and different networks would function way faster due to enhanced optical speeds. But at the same time, the sun would also become much hotter, around 1 million times hotter. And it would mean only one thing: Earth would be boiled in no time. So we should probably be grateful for our slow speed of light. If it were even a bit faster, our planet wouldn't exist.
The simplest way I can explain the concept of a wormhole is this. Try to picture a real earthworm eating its way through an apple. At one point, you'll see one part of the wormhole sticking through the top of the fruit, while its rear end is poking through the bottom. In this example, the worm itself acts like a tunnel, which connects two places in space, or two different places in time, or even a combination of both. In theory, a wormhole could help you travel to the same place you're at right now, but years ago, or instantly transport you to another continent. It can also help you travel back to when the ancient pyramids were being constructed. The concept was first theorized in 1916. Though back then, people didn't call them wormholes. It was then studied by Einstein and his fellow scientist Nathan Rosen back in 1935. But it all started with Einstein's theory of general relativity. He had a hunch that Isaac Newton's idea of gravity as a force wasn't completely right. So he began working on many different experiments to prove his theory. In the simplest of terms, Einstein's theory of general relativity says that gravity is a curving or warping of space. The more mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. Because of the ball's mass, the rubber sheet under it is warped under the weight. It's the same with our sun. It's big enough to curb space across our solar system. That's why our planet and other objects surrounding us orbit around the star. Now, let's keep our attention on the same trampoline. If there's no pressure applied to it, its surface stays flat. Now imagine 2 points on this fabric, symmetrically placed on each side of the trampoline. Looking at them from this perspective, there's no possibility of them ever touching each other. But if an object is heavy enough, this flexible fabric can stretch so much that 2 points might potentially meet. The tunnel between those 2 points would be a wormhole. They're basically bridges that connect two places in the fabric of space and time that have no chance of ever meeting in normal circumstances. Wormholes can also be seen as shortcuts. Problem is, we don't have any of these wormholes in our universe, or at least none that we know of. Scientists have no proof so far that they exist, and we also don't have any idea how they can form to begin with. What we do know so far is that they could, theoretically, exist. To move forward with our story about wormholes, we also need to talk about black holes. They're points in space where gravity has so much force that even light cannot escape them. Gravity here becomes so intense that matter gets squeezed into a tiny space. We know that this can happen when a star, like the sun, is dying. At the beginning of their lives, a star's hydrogen ignites in its dense, hot core. Because of its gravity, it tries to draw in its own mass into a tiny point. But as long as it has the energy generated by hydrogen fusion, it also pushes objects outward. If we look at it this way, the life of a star is a delicate balance of forces that can last millions or even trillions of years. These forces are also the ones keeping our planet in place and making sure we move constantly at the same speed and trajectory. Once that star's energy is exhausted, the only force remaining is that of gravity. Hence, some stars, those that are big enough, become black holes. Since light itself cannot escape their force, we people can't visualize black holes. For the human eye, they're invisible. We need special tools with unique telescopes to help us point them out in the universe. Now back to the wormholes. We have yet to see what a wormhole looks like. But scientists have theorized that they are extremely unstable. Why? Because in simple terms, they're made out of a black hole and a white hole touching each other. Okay, what? And as far as we've studied them by now, black holes at one point become infinitely dense and the pressure becomes unimaginable. Once you enter a black hole, there's little chance you'll make it out the other side. Some astronomers say that even if we could find a wormhole, and we could technically enter it, and it would rapidly collapse on itself. Even the tiniest bit of extra mass, like that of our bodies for example, can result in the wormhole popping out like a rubber band that's been stretched too hard. So, wormholes, huh? We haven't seen them, but we do have some math that can back them up. Black holes? We can't technically see them ourselves, but we do have some gadgets that can help us with that. But there are some theories about the universe out there that might have caught your eye in the past too. If you've watched the movie Matrix, you might have heard about the simulation theory. This is one of those hypotheses that doesn't come from scientists, but rather from philosophers. We know that all the information we have surrounding us, sounds, images, texts, and textures of the things we touch, are translated to us by our brains. If our brains are the windows to the outside world, who is to say we aren't living inside an illusion? It may sound outrageous, but some famous thinkers of the world have really considered this possibility. The simulation theory can't be listed as a truly scientific one. If it fails the basic test, there's no way to prove if it's true or false. What about life on other planets? There are many scientific projects taking place all over the world looking at ways humankind can survive outside the Earth, should we ever have to. Like the Hot and Mars project, which is taking place on Devon Island, located in the Canadian Arctic archipelago. Conditions here are so harsh that scientists believe if we can make it here, we can survive on Mars too. That's because the soil stays frozen throughout the seasons. Also, the eastern part of the island is covered by a thick ice cap all year round. Since almost no plants are growing here, there are no animals that could have adapted to these conditions. Despite all the scientific effort, some seem to believe there's some sort of life form on Mars already. NASA's Perseverance and Curiosity rovers take regular pictures of the reddish planet's surface. You can check out these pictures on the internet for yourself if you want to. Over time, some odd shapes have appeared here and there in these pictures, making some people believe people are living there already. Back in 2008, one of the rovers took a picture of a rock that looked very much like a female figure. Other photos seem to show animal-shaped figures, utensils, or other Earth-like objects. Again, there's little to no proof of this theory, as rocks can be of all sorts of shapes and sizes. And if you look at the pictures, it does make you wonder. We may find it hard to travel way over there, but we can theorize that our observable universe has an edge and an ending. This fact raised a question for many scientists and philosophers. Could our universe be just one of many existing in a multiverse? One possible scenario depicted to explain the multiverse is trying to imagine a bunch of universes as separate bubbles, constantly coming to be and moving. Since we haven't figured out all the features of the universe we live in, who's to say there aren't many more? As interesting as this theory might be, we have no observable evidence that we live in a world with multiple universes. So far, we can just imagine different bubbles of time and space, where the rules of physics might be different. Some might lack gravity, while others may exist without ever seeing the light. Scott Kelly is a lot of things. An American engineer, a retired astronaut, and a time traveler. Wait, what? Kelly commanded the International Space Station on several missions. On one of those trips, he spent 340 days aboard the giant, floating science lab orbiting Earth. While he was up there, improving the water recycling system, testing heat transfer in microgravity, and doing all the other genius-level stuff astronauts do, he was also aging. But not like you, me, or even his identical twin brother Mark. He was actually aging slower than all of us. Okay, so both brothers are astronauts and have been to the International Space Station, but Scott spent way more time up there. About 10 times as long, actually. And here's where things get more interesting. Even though Mark was born 6 minutes before Scott, he is now 6 minutes and 5 milliseconds older. That happened because Scott aged a little more slowly while he was orbiting the Earth. And astronauts age slower because they're moving much faster than us, at 17,500 miles per hour. Basically, the faster you go, the more time stretches out. So the closer you get to traveling at the speed of light, the slower you age. From Scott Kelly's perspective, nothing felt unusual up there. Time passed like normal for him. But he actually aged less than his twin brother over the same period of Earth time. So when he returned, we can say that he had essentially leapt forward in time, relative to us. So, if traveling close to the speed of light lets us leap forward in time, that means astronauts have already kind of achieved time travel. Sure, it's a bit of a letdown that it doesn't happen like Back to the Future, hopping into a cool futuristic car and zipping into another timeline. But this is real, at least according to some scientists. Real time travel isn't about jumping from one moment in time to another, like going back to the age of the dinosaurs, then hitting a button to fast forward to the year 2100. The time travel that's possible today is more about actually living into the future. It's about moving faster than 1 second per second, just like Scott Kelly did. To explain the theory behind this wild idea, we have to bring a celebrity into the conversation: Albert Einstein. Think about your childhood and your retirement. Whether it's in your past or your future, time always ticks at the same steady rate. But then along comes Einstein saying, sure, but it's not that simple. He introduced the idea that time is relative. In other words, the amount of time you experience compared to someone else depends on what you're both doing. And where exactly you are in the universe. Time is not the same for everyone. Here's an example. You're sitting on a bench, holding a melting ice cream cone. Meanwhile, your friend zooms past in a super fast spaceship. For you, maybe the ice cream melts in 5 minutes, but for your friend flying at a crazy speed, this same scene took less time on his watch. That's time dilation. Time actually moves slower for things that are moving faster. That's the heart of what's known as special relativity. We actually proved Einstein's theory back in the 70s. 2 scientists took super accurate atomic clocks and flew them around the world on planes, first going east, then west. They compared those clocks to a third one that stayed on the ground. When all 3 were brought back together, they showed different times. The clock that flew east in the direction of Earth's rotation lost 59 nanoseconds, and it was moving faster relative to the ground. The one that flew west against Earth's rotation was moving slower, so it gained 237 nanoseconds. Now, think about those astronauts living in space moving way faster than we are. They travel at about 5 miles per second, orbiting Earth roughly every 90 minutes. If you do the math, spending 1,000 days up there lets you skip about 0.027 seconds into the future. I know that doesn't sound like much, but that's because the speed of the ISS is tiny compared to the speed of light. Still, if we keep going with that idea, it pretty much makes the astronaut Oleg Kononenko humanity's greatest time traveler. In 2024, he set the world record for the most time spent in space: 878 days in orbit. Okay, so we now know that Kelly and Kononenko are, in a way, living in the future. But what about traveling backward in time? Well, I'm sorry to say, traveling back to your glorious high school days is a whole lot trickier. In theory, we could, but in practice, it's pretty much impossible. Imagine space and time as this big, stretchy fabric, and gravity is what bends it. Kind of like when you put a heavy bowling ball on a trampoline. In theory, if you could bend it just right, you might create a shortcut through space and time called a wormhole. a tunnel that connects two different points. Let's say the present and the past. Now, usually, gravity pulls things inward. It wants to collapse tunnels, not keep them open. So the walls of this tunnel are constantly under pressure from the universe, trying to squish them shut. To stop that from happening, and to keep the tunnel open long enough for something or someone to go through and get to the past, you'd need something that pushes outward, against the collapse. And that's where negative mass comes in. Negative mass is a weird theoretical idea in physics. Unlike regular mass, which pulls things together with gravity, negative mass would actually repel things. It would push away instead of pulling in. It's like using anti-gravity to keep the tunnel from closing. It would act like braces, holding the tunnel open from the inside. But here's the problem. We have never actually seen negative mass. It's just something that might exist on paper, in math, but no one's ever found any in real life. Plus, there's something called the self-consistency principle. Basically, it says that time travelers can't create time paradoxes, like those crazy scenarios in the Butterfly Effect movie. Let's say you go back in time to stop your granddad from meeting your grandmother. But here's the problem. If they never met, that means your parents were never born. And if they weren't born, well, how do you exist? That's a time paradox. Something that causes all sorts of inconsistencies in the universe, making everything a total mess. And according to the self-consistency principle, that's impossible. It just can't happen. Some specialists, though, think they have an answer to the grandfather paradox. All we need to do is think about time as an endless loop with no starting point. In a closed time-like curve, as this theory is called, the past and present blend together in an eternal time loop. There's no way out. There's no changing things. It would all look the same if played in reverse. For example, what did you do yesterday? Let's say you woke up, brushed your teeth, worked all day, had your meals, and then went to bed again. Following the closed timeline curve theory, if you could go back to yesterday, you'd do those exact same things in the same order, no matter how hard you try to take the day off. Because in a closed time-like curve, you're retracting not just your steps, but every single second of reality itself. And that's the only way time travel could be possible. So, even if we somehow manage to build a time machine, and even if we give it our best shot to change the past, nature will always find a way to prevent contradictions. In the end, everything would have to align perfectly to keep our history from becoming a mess.
So you're standing on a diving board in the middle of an open space. You look down, but that's not a pool. It's a giant black hole. Well, what the heck? You start swinging and then you jump. The gravity of the black hole grabs you, and you pick up speed. Just a little more, and you'll enter the dark abyss. But you're not afraid. You're sure you can survive the fall into the black hole. Besides, you have a clear goal to travel through time. But first, let's figure out how it works and why time stops near a black hole. This is the space-time grid. It's what our entire universe is made of. And just like a regular grid, it sags if you put something heavy on it, like me. For example, let's put the planet Earth here. You see a little funnel that is formed around the Earth. And if you put a small ball next to the planet, it'll roll into the funnel. That's how gravity works. The heavier the object, the more it bends space-time. By comparison, here's the Sun. It's almost 333,000 times heavier than the Earth, so it makes a really big funnel. So big that all the planets in our solar system move around that star inside that funnel. So now, let's put a black hole on a space-time grid. Its centers are infinitely heavy, so they create a limitless deep well. And anything caught in the black hole's gravitational field can never leave it, not even moving at the speed of light. Okay, their gravity is infinitely strong, but why do they slow down time? It's all about the speed of light. According to physics law, the speed of light must be the same at every point in our universe, even in a black hole. So, for our experiment, we take this ball, a photon of light that can travel 671 million miles per hour. You could get from Earth to the Sun at that speed in 8 minutes. That's how long it takes light to travel from our star to our eyes. So, when you're looking at the Sun, you're looking back in time 8 minutes ago. By the way, don't look at it directly. Now, the critical thing to remember here is that velocity consists of two physical quantities: space, miles, and time, hours. We'll use that later. Now, let's look at the black hole in our space-time grid. In three-dimensional space, it appears like this. But if we assume that space is two-dimensional, our grid looks like this when viewed from above, just a lot of squares. And this is the black hole right in the middle. If you look at the grid from the side, you'll see a straight line. And the black hole here looks like a pit, or like an endless well. Now, let's follow our photon of light in three-dimensional space. Here, it's moving toward the black hole, and then it falls into the well of the black hole, and it continues its motion at a constant speed. Now, the side view. Again, the photon moves from left to right and then falls. Its velocity doesn't change. The problems begin if you look at the experiment from above. When the photon of light moves in the distance of the black hole, its speed is stable. But then it goes down into the well. First, it slows down and then it just stands still. But it's moving downwards. The photon moves in an arc down the well in the lower dimension without changing its speed. But in the higher dimension, it traveled a minimal distance at the same speed. Usually, this would mean that the photon was moving at a low speed in the second case, but not in the case of the speed of light. Remember, it must be the same at every point in the universe. The number 671 million miles per hour shouldn't change. So, we change the very parameters of that number: time. Time itself must slow down so much that this slight movement of the photon, when you look at it from above, was at the same speed, 671 million miles per hour. But if you go down and look at this well much lower, you see that its walls are almost vertical. So, a photon of light would be moving in a vertical trajectory. That means that if you look at it from above, the photon will just be standing still. Again, its velocity can't change, so time will vary. At that point, it should just stop. This is what happens near a black hole. Now, if you look at a black hole, you can see this effect in action. It swallows up the light around it. But as for an observer, it seems to you that the light stays in orbit around the black disk. In fact, at that moment, the photons are still moving at the speed of light inside the black hole. It's because time has slowed down there so much that you feel like the light has stopped there. This disk is called the event horizon, the point of no return, the last stop before you go into the black abyss. And at the very center of the black hole is the singularity. This point of space is so dense that if you tried to describe it with any numbers or physical quantities, they would all tend toward infinity. Simply put, all the laws of physics we know just stop working here. So scientists can't say exactly what awaits you in the singularity. Before you make that jump into the black hole, let's drop a space probe there with a blue light that flashes once per second, and let's attach giant clocks to it. You see the probe falling into the black hole, gaining speed. But then it starts to slow down. Moreover, the probe flattens out and seems to spread out around the black hole. And then you notice that the blue beacon on the probe has changed its light. It now flashes as red. It's because the light is a wave. Blue is a truly short wave with a high frequency. But the black hole's gravity acts on this wave, stretching it out. The light waves get lengthened and become broader and less frequent. The new wavelength and frequency match with the red color. It's called redshift. Also, the probe blinks now not once a second in short beeps, but lights up and goes out for a long time. It's because of the time warp. If you, as an observer, look at the clock on the probe, the second hand there barely moves. However, the clock on your hand works as usual. But if you could be in a black hole, time would seem normal to you, and the arrow on the clock would move as it did before. But the hands on the clock outside the black hole would move like crazy to you. That's because time goes much faster outside the black hole. Oops! Your probe just got ripped apart. That's because of the substantial difference in gravity that acts on the probe. The black hole's gravitational force increases with every foot of approach. That is, if you were to extend your hand toward the black hole hard, the gravity on your fingers would be much stronger than on your shoulder. This force would cause your fingers to lengthen, simply like spaghetti. That's why many people think it's impossible to survive falling into a black hole. But scientists think you could survive without a problem. Hey, maybe they should jump first just to make sure. The thing is, you have to pick a black hole as big as possible, like the ones at the centers of galaxies, for example. That bright spot at the center of the Milky Way also has a black hole. It's about 1 million times heavier than the Sun. And this is the Messier 87 galaxy, one of the most massive galaxies among our neighbors. In 2019, humanity got its first ever photo of the black hole at the center of this galaxy. It's about 6.5 billion times heavier than our Sun. So, it's the perfect place to make your jump into a black hole finally. Let's go. At first, you feel a strong acceleration as the incredible force of gravity grabs you. But in the case of a supermassive black hole like this, the gravity doesn't change as dramatically. That's because of its size. Right now, the gravitational force on your legs is about equal to the gravitational force on your head, so you don't turn into spaghetti, and you feel comfortable. You see that the light from the stars and all the space around you has begun to shrink at a certain point. It means that you have already passed the event horizon and are now moving toward the black hole's heart. As a result, the light of the universe becomes a small dot for you and then disappears altogether. If we look at our space-time grid, you're already falling into a well. Time is completely stopped for you. However, the rest of the world continues to move steadily through time. If you could now look at the Earth from a black hole, you would see a time-lapse, an accelerated video of how the months and years go by on our planet. If you had a jetpack that had an incredible engine to pull you out of the black hole, then you can make a jump forward in time. In 1 second, centuries on Earth could pass in the heart of a supermassive black hole. But this only works one way. You can't go back in time. But for now, you keep falling into the black hole. Beyond that, no one knows what'll happen to you. We only have theories about wormholes and white holes that might transfer you somewhere else in the universe. So, enjoy your trip, and just think about all the frequent flyer miles you're racking up. We're traveling 1,000 light-years from our planet to an unfamiliar system. Here, there are 2 bright stars orbiting close to each other. But there is one small but very massive thing here as well – a black hole. These objects are mysterious and dangerous. They're capable of swallowing our entire world in 1 second without even noticing it. Even more, they can tear apart a huge star like our Sun. And it's these giants that usually lie at the centers of galaxies. They're so heavy that their gravity holds countless stars, planets, and stardust around them. They can weigh millions or even billions of times more than the Sun. And now, you're back on the ground, at a rocket launch pad on Earth. All you can think about is holding your breath and jumping into the heart of that black pearl. But you don't have to hold your breath because you'll be in a spacesuit, and the oxygen is included free of charge. Besides, you're not likely to ever make it to the black hole. A trip that far with the technology we have now would take tens of thousands of years. Back to your garage where you stashed your hyper rocket, which will take you to the black hole in seconds. And you're next to 2 stars in a black hole. First thing you notice is that the black holes aren't black. Its gravitational force pulls in not only objects, but even light itself. This makes the hole invisible. You can only see a bright ring around it. That's called the event horizon. It consists of twisted light, hot dust, plasma, and pieces of asteroids that are also trapped there. So the event horizon is the first obstacle to overcome. Okay, you put on your jetpack, open your rocket's door, and jump towards the black hole. The force of gravity begins to pull you quickly toward it. The spacesuit protects you from the enormous temperatures and levels of radiation on the event horizon. Conventional protective gear would hardly help you, so you thank your dad for stashing this super powerful protective suit in your garage as well. you begin to feel like your body's stretching unpleasantly. The problem is that gravity increases with every inch closer to the center of the black hole, and it's much stronger at your head than at your feet. Your body starts to stretch like spaghetti. That's why it's called spaghettification. No suit can protect you from that, and there isn't a single spaceship that can withstand that kind of strain. Well, this was a short video. Okay, let's rewind to the moment before the jump. You realize that to get to the heart of the black hole and survive, you don't need improved equipment, but another black hole. And it's the size and weight of it that matters here. Theoretically, you can survive falling into a supermassive black hole. It's all about the width of the black hole's event horizon. When a hole is small, about the weight of our sun, the event horizon is small too. And then its edge is remarkably close to the center of the abnormal gravitational force, which would make you spaghettified quickly and brutally. But if the event horizon is wide, it's farther from the center of the gravitational force. Then the difference of gravity pressing on your head and feet will be non-existent. So if you have enough air in your spacesuit, you can survive such a journey. So you must pick a supermassive black hole. Let's see. One at the center of the Milky Way? No, there's too much hot plasma and debris around it. You need a completely isolated black hole for a jump like this. Somewhere in dark space where it hasn't had time to gather the debris of neighboring worlds around it. You quickly open your space map and find such a black hole. One faster than light trip, and you've arrived. There it is! A huge dark nothing. There's only distorted light from distant stars and galaxies on its event horizon. To test your theory, you throw a mannequin into it. It approaches the black hole and then slows to a standstill. But it's just an illusion. The black hole is so heavy it can warp both space and time. So, to the observer, the dummy is frozen in the event horizon, but it has long since entered its heart. The dummy didn't get spaghettified like you did when you fell into a small black hole, so now you're confidently jumping after it. Remember that even if you feel fine, it's still a one-way trip. Once in the black hole's field of attraction, nothing can escape its embrace, no matter how powerful a rocket you have or how hard you flap your arm. You're now at the edge of the accretion disk. Every second here equals weeks or months on Earth. You're traveling through time. Our home planet may already have flying cars and skyscrapers several miles tall all over the place. But for you, it's only a couple of minutes. Whoa! All the light you see from the stars has turned red. That too is because of gravity. The light we see is waves, but the black hole stretches them out. The short wavelengths of blue become long and red. Great! You've passed the event horizon and are now heading into black nothingness. You look up and see a thin ray of light. The last thing you see, in fact. After that, there's just black void. No one knows what happens next. Some theories say black holes can be portals to another dimension, or to another place in the universe. By jumping into a black hole in our galaxy, you can jump hundreds of thousands of light years away from our home. In that case, you will experience your fall in reverse. First, you see a small but expanding beam of light. Then, red starlight returns to blue. And before you know it, you're back on the event horizon. And soon after, you're free of the black hole's pool. But scientists still can't confirm this theory. Okay, that's too grim. So just this time, we'll bring you back to Earth in the company of your friends. They praise you for your accomplishment of surviving the center of a black hole. Now you're the heart of the company, and no black hole can scare you. But even the biggest black hole in space isn't as scary as you might think. They have a lifespan. That radiation I mentioned takes energy from the black hole. If it doesn't have food around it, the hole starts to deflate like a balloon, and eventually there's nothing left. Another fear around black holes is that we can create one at home. Indeed, inside the Large Hadron Collider, scientists conduct experiments with small particles colliding at high speed. There are huge bursts of energy, and some scientists believe this energy is enough to create a microscopic black hole. It will begin to absorb its surroundings and grow. First, some small objects in the room where it was created, then the entire lab. The hole continues to grow and is already consuming our whole planet. It changes the balance of power in our solar system and absorbs the planets one by one. When those are finished, it's time for dessert, the sun. The light upper layers of plasma are stretched into long spaghetti and pulled toward the black hole. Then, layer by layer, our star collapses into the dark abyss. When the sun is half absorbed, the black hole shoots a beam of energy and light outwards and continues to consume the sun. In mere moments, there's nothing left of our solar system. That's how some people describe the end of the world. But even if we do manage to create a microscopic black hole, we'll be safe. It'll be too small to absorb big objects, and it will only feed on small atomic particles. Black holes emit energy as well as consume it, so our little one won't have time to grow. It'll lose more than it finds in a fraction of a second. So what you'll see is a momentary flash and then nothing. Although creating a stable and controlled black hole may even be useful, they emit enormous amounts of energy that we can use. A black hole the mass of Mount Everest could power all of humanity. Of course, black holes are still dangerous, but we can watch them and study our universe. If we stay far enough away, of course. So, you decide to put a padlock on that garage door. For now. So, do you know why the ocean is salty? We didn't know the reason until 1979. The whole planet is covered with ocean, and we had no idea where all that salt comes from. We initially thought rivers were to blame because they can carry deposits and chemicals to the still waters. It wasn't until the late 1970s when scientists stumbled upon so-called black smokers that we realized they were the cause of the salty waters. They are, in fact, geothermal vents located along the mid-ocean ridge. They were generated from sediments of iron sulfide from deep within the Earth's core. Okay, remember dinosaurs? I don't. I wasn't around then. But they disappeared a long time ago. Yet how that happened was still up for debate within the scientific community for a very long time. Up until 1991, no less, the year the Chicxulub crater was discovered. That's a big hole located underneath the Yucatan Peninsula in Mexico. Many claim it was formed when a giant asteroid crashed on Earth. The oldest material ever found on our planet turns out to be older than our entire solar system. The Murchison meteorite plopped into Australia back in September 1969. But we made this staggering discovery after a newer analysis of its debris was done only in 2020. Did you know that there is a coral skyscraper hidden underneath the ocean, and we had no idea? Only in 2020, a team of Australian scientists stumbled upon it when mapping the northern Great Barrier Reef. It's 1,640 feet tall, which, if you think about it, makes it taller than the Empire State Building, and no elevators. Do you know how mountains appeared? We didn't know that until 1966. And that also concerns earthquakes and volcanoes. Just think about it. We sent men into space before we even understood how and why the Earth under our feet started moving now and then. Only in 1966, a scientist named J. Tuzo Wilson published a piece in the journal Nature in which he explained that continents and oceans are constantly moving. He also wrote about tectonic activity, meaning things like earthquakes and how mountains rose from the Earth's surface. Until 2021, we hadn't mapped out a full human genome sequence. The concept of DNA was first presented by a Swiss scientist back in 1869, but specialists remained partially in the dark as to DNA's physical structure until Rosalind Franklin and Raymond Gosling took pictures of it and found it looked like two twisting strands. Ever wonder what the largest living organism in the world was? For a long time, scientists did too, because they only stumbled upon it in 2000. It's a fungus that lives 3 feet underground, but is estimated to spread across 2,200 acres. Located in the Malheur National Forest in the Blue Mountains of eastern Oregon, it's named the honey mushroom. Until 2002, we didn't know what was at the center of our galaxy, the Milky Way. We knew we were rotating around something, but it took us until the 21st century to figure out it was a supermassive black hole, with a mass 4 million times bigger than our Sun, located in a region of the Milky Way called Sagittarius A star. The discovery took place after we came up with the infrared smoke alarm. I can hardly imagine having to travel long distances without wheeled luggage, but these didn't pop up until 1970. If you think about it, the astronauts who went to the moon actually had to carry their baggage in the spaceship physically. The application for the U.S. patent for the wheeled luggage was granted back in 1972, but to be fair, those first ones weren't exceptionally reliable. They had problems like wobbling and tipping because the large suitcases were mounted on narrow-wheeled bottoms. If you look at pictures of 1940s film stars, you'll see that their hair was nice and slicked back. Did you know that based on recent discoveries, even ancient Egyptians used some hair-molding substance? What they used, though, wasn't hair gel, if that's what you're thinking, because we only came up with this invention in the 1960s. What people used for hairstyling back then in the 1940s was called Brill cream, which had more of a waxy consistency and was invented in 1929. Hair gel, as we know it today, came a bit later and was invented by a man named Louis Montoya. It soon became trendy because it wasn't as greasy as previous products. Speaking of bathrooms, and I am about to, back in ancient Roman times, they used some sort of, wiping devices, but they were sticks with a sponge on top. Individually perfumed sheets of paper that had the same purpose appear to have been documented in China back in 589 CE. However, in the US, medicated paper for the water closet was marketed in the late 1850s, but the soft and comfortable variant of toilet paper was commercialized only in the 1930s, with the added bonus of being completely splinter-free. And I think we can all appreciate that. This one may not seem so recent, but hear me out. Modern research revealed that Saturn's rings are less than 100 million years old or so. That may seem like a lot, but if you think that the solar system formed about 4.5 billion years ago, it does shift your perception a bit, right? There are species of sharks on Earth that have been around in our waters 4 times longer than Saturn's rings. We figured this out using recent data regarding the mass of Saturn's rings and their ratio of dust and ice. With many of us resorting to e-commerce more and more these days, it's challenging to look at the traditional supermarket as some revolutionary invention. But we didn't have these for as long as you'd think either. Do you know how the first supermarket appeared? Well, back in 1916, a shop owner named Clarence Saunders needed a solution to make his job less labor-intensive, since shopping around then meant he had to pick out all the products from the aisles and even deliver them to customers. So he thought about a new shop layout with a turnstile entry. People had to browse the shop in a single direction. He also made sure they were passing by all the available products. Customers could pick their items themselves and had to take their produce home. The shop owner could lower his prices with added efficiency, since he needed fewer people to run the business. Did you know there's still a state in the US where wearing a seatbelt isn't mandatory? Historically, using a seatbelt was voluntary, but people being the way they were, safety needed some enforcement. The state of New York was the first one to pass a law that enforced seatbelt wearing while driving, but only on December 1st, 1984. Still, to this day in New Hampshire, there are no laws on the matter. The modern can opener, the one with the spinning wheel, was first introduced to the market in 1870. Now, that may not be remarkable, but it seems odd when you think canned foods were already available for some decades. Before this invention, we were told to literally cut around the top of the can near the outer edge with a chisel and hammer. You got a meal and an excellent workout all in one. Did you know that standardized time became enforceable by law only in 1880? The current system that we use now, GMT, for Greenwich Mean Time, became a common practice in most countries even later, somewhere by the end of the 1920s. Now, we used to estimate what time it was by looking at the sun's position in the sky. We then evolved to using clocks, but they were still dependent on the sun's position in a particular town or village. That meant time could differ slightly between two neighboring communities. And it wasn't that big of a deal for us until the invention of trains. As we started to travel faster and on longer distances, we needed to figure out a way to know when a train would leave and reach a certain destination, which could be helpful for all travelers in various locations. And frankly, it was about time.
Our Sun. Scenario 1. Something strange just happened now. Every TV channel, the news, they're all talking about a black hole that came closer to us, on the spot where our sun used to be. You can even see an accretion disk, and the background of the sky looks kind of distorted, which means it got really close. Normally, black holes are so far away that we can't see them with the unaided eye. You can't even see them with a telescope directly. What's it doing here so close? And where's the sun? Did the black hole swallow it? The sun used to be in the center of our solar system, far enough not to burn us, but still close enough to give us light, warmth, and beautiful scenes when it rises in the east and goes to rest in the west. Hey, this one even rhymes. Well, it gave us life. The most massive body in our solar system contains 99.8% of its total mass. It's so wide, you could fit more than 1 million Earths inside of the sun. Maybe our sun turned into a black hole, but it's way too early for that to happen. I mean, that's how they form, when enormous stars come to the end of their life cycle and explode, which is called a supernova. They end up collapsing on themselves, becoming very small. It's a tiny size and a huge mass. That's what makes black holes' gravity so strong, and even light that comes too close can't escape. And all the stars in the universe are shrinking and will disappear at some moment. Our sun loses 4 million tons of mass every second, and eventually, the only energy left in the universe will be generated by black holes. A black hole is surrounded by dust, gas, and radiation. The radiation is very dangerous, so we hope our planet won't come near it. Our solar system doesn't have light anymore. No light and no heat either, so even Mercury and Venus will probably get covered in ice pretty soon, not to mention Earth. Do I need to say nothing will survive this new ice age? The only salvation might come from the accretion disk that spins so fast it generates heat, but that's too many chances to take. Still, at least if the black hole has the same exact mass as the sun before it, all the planets will remain in the same orbits, Earth included. But if it has a mass bigger than our sun, which is something our scientists are currently trying to figure out, then bye-bye, solar system. It was nice knowing you. Scenario 2. Oh no, what's happening? It was supposed to be a nice sunny day, but now you see darkness descending so abruptly. How come it's night, yet the clock says it's 2 p.m., and the moon looks different? The TV reports say our sun is gone, and due to some mysterious events, the moon is not orbiting the Earth anymore. It's in the center of our solar system now. We don't have much time left. Since the sun is not in the center of our solar system, we now have 8 minutes and 20 seconds to become aware of it. It may take millions of years for the sun's energy to travel from its core to the surface, but 8 minutes and 20 seconds is exactly how long it takes for sunlight to reach Earth. The light takes a journey across 93 million miles, which is the distance that separates us from the sun. We're not in the habitable zone anymore. The habitable zone is the distance from a star, in our case, the sun, at which liquid water could exist on the surface of a planet. Now that the sun's gone, its light won't reach us anymore, and our planet will gradually become a frozen, lifeless rock. Who knows if we'll have enough time to come up with some technologies that would provide us with the solar energy we need to sustain life on Earth. If not, well, millions or billions of years later, scientists from some other civilizations would explore it, trying to find evidence if life ever even existed there. It would be the same as we do with Mars and other planets in our solar system, trying to figure out if they've always been lifeless or if there might be a sign that some organisms used to live there. something else, also vital for our life, travels at the speed of light. Gravity. Without the sun, for roughly 8 more minutes, the planets would continue circling the empty center of our solar system until the clock ticks and they finally drift somewhere into an unknown direction of outer space. Our moon doesn't have a strong enough gravity to keep us in place. It can't shine so brightly to give us warmth and support life. It's so far, we can barely see it now. Without the moon that peacefully travels close to our planet as it used to, we can see tides are getting lower incredibly fast. Oh, and it's becoming really windy. Winds are so much stronger and faster now. When things were normal, our planet sat at a 23.5 degree tilt, which is the reason we had changing weather and seasons. Now the tilt is so extreme, it's getting very cold, very fast. And our time is almost up. People are screaming, everyone's in panic. We still have maybe 1 minute left until we sink into eternal darkness. Scenario number 3. We're not sure what exactly happened and how the life we carelessly lived yesterday came to an end. No one could predict it, but it seems that, out of nowhere, a giant neutron star took the spot where our sun used to be. It's not something we'd recognize on our own. We just noticed something was different, and the sun kinda got smaller and weirder. The rest we heard on the news, and no one knows how it happened. Maybe our sun is somewhere behind the neutron star. Or the star pushed it out of our solar system and into an unknown direction? A neutron star is the densest space object we know about. It has almost twice as much mass as our sun, but it's all squeezed into a star only 10 miles, 15 kilometers, across, which is about the size of a city on Earth. A neutron star forms when a huge star runs out of fuel. It collapses in a big explosion. Its very central region, the core, collapses, which is why every electron, negatively charged particle, and proton, positively charged particle, crush together into a neutron, which is either uncharged or neutrally charged. We're in a very tricky situation now, basically waiting for our end to come. This neutron star has gravity 2 billion times stronger than the one Earth has. This means our new sun will pull all the planets in our solar system towards itself and eventually destroy them. It's already started. For the first time that we know of, the planets are leaving their stable orbits, attracted by the powerful force of the neutron star. It's becoming chaotic pretty fast. And it won't stop there. A neutron star rotates more than 700 times every second, which is incredibly fast. Our sun rotates once every 27 days. So, after it destroys all the planets, including us, this star will continue whirling throughout the universe at about 1/5 the speed of light. Maybe it will slow down and fizzle out with time, but maybe not. After thousands of years, many neutron stars begin to slow down and blow out. But that doesn't always happen. If it meets another star, it will orbit it and start to feed off its atmosphere until it collapses at some point and turns into a giant black hole. Our sun was going to burn out anyway. Until the neutron star showed up, the sun was 4.6 billion years old, which was about halfway through its lifespan. It had already burned off about half of its hydrogen stores and had enough supplies for another 5 billion years. It was eventually supposed to end up the size of the Earth. After running out of fuel, it would have simply collapsed. It would have retained its enormous mass, but its volume was going to be similar to that of our planet. No sun, no life, so the result would have been basically the same. But this way, it would have been a slow process. Who knows if humans would even inhabit this solar system in those times? But with neutron stars, things move towards the end pretty quickly, and it's way more chaotic. If the neutron star was going crazy somewhere far away in another galaxy, we'd only see it in the shape of a distant flashing light that we call a pulsar. But this way, boom! There's only one star in our solar system, the Sun. And all the planets orbit this star. But there are also systems where a planet orbits 2 suns. For example, Kepler 16b. It's an inhospitable and cold place, made of half rock, half gas. But the coolest thing there is that if you visited this planet, you'd see 2 sunsets and have 2 shadows. But astronomers seem to have found something rarer and more bizarre. There might be a planet that orbits 3 stars at once. The GW Orionis star system is around 1,300 light-years away from our planet. It's composed of 3 orange rings. They're made of dust and nested inside one another. In the center of this system, you can see 3 stars. 2 of these stars are binary. It means they orbit each other. The third star revolves around them. Scientists have found out that the 3 rings are misaligned. The innermost ring swings widely in its orbit, and the outermost ring has a tilt of 38 degrees. So, astronomers came up with 2 theories. The first theory says the break in these rings occurred because 3 suns created torque at the center of the entire system. Torque is a gravitational force that always acts toward the center. But sometime later, this theory was written off. There wasn't enough turbulence in these rings for this theory to work. The second theory claimed that this phenomenon could be happening because a planet formed inside one of these rings. A young planet could affect the gravitational balance of the 3-ring system and be the reason they were spread so far apart. There's a specific gap in the dust cloud. Based on its size, the planet we're talking about must be a large gas giant the size of our Jupiter. All space objects have been formed thanks to gravity pulling matter together. If there's even the slightest rotation at the beginning, the spin rate increases with time, especially when an object starts collapsing. That's why all space objects rotate, including dust particles and even black holes. Black holes lose their mass because of a thing called Hawking radiation. Their event horizons are becoming smaller, but this process is very, very slow. A black hole's event horizon is a point of no return. It's like a boundary that surrounds a black hole, and nothing, including light and radiation, can escape once it crosses this boundary. The average black hole would need billions of times the age of our universe to disappear completely. Our home Milky Way galaxy might also contain a supermassive black hole, but we're in no danger. One of the closest large black holes, V4647 Sagittarii, is most likely 20,000 light-years away. It's safe to observe the effects black holes create from a distance. Problems start when you get too close because of their mind-boggling gravitational force. Galaxies can consume one another, which is one of the ways how they evolve over time. Our closest neighbor is called Andromeda, and it's currently munching on one of its satellite galaxies. In the past, Andromeda ate at least 2 others. Plenty of star clusters are scattered all over this galaxy. Andromeda must have stolen these stars from other galaxies. Scientists have finally managed to identify those stars. They have tracked them back to galaxy mergers that happened billions of years ago. 10 billion years ago, our home galaxy also went through a collision. That's why now its halo isn't like the ones other spiral galaxies have. Scientists first thought it was several small collisions, but then they realized that most of these space objects in the Milky Way came from a single source. It was another galaxy, Enceladus, that the Milky Way collided with. The Milky Way and Andromeda galaxy might collide, but it's unlikely to happen in the next 4.5 billion years. Neutrinos are electrically neutral particles that are so powerful that they can go through miles and miles of lead, and nothing will stop them. Some of them are passing through your body as you're watching this. Neutrinos get formed both in the nuclear reactions inside alive stars and in the supernova explosions when stars go out. These particles are nearly massless. They need less than 3 seconds to get to the surface of the sun, and then they can reach our planet in only 8 minutes. There's a planet, TOI 1231b, around 90 light-years away from Earth. It's similar to our Neptune. It's a gas giant, but the most interesting thing is that this planet is likely to be rich in atmosphere. The planet is over 3.5 times as large as Earth and a bit warmer than we're used to, 134 degrees Fahrenheit. It orbits a red dwarf star, way smaller than our sun. But this star is also much older. 1 year on the planet is only 24 Earth days long. Even though the planet is close to its parent star, it remains relatively cold. That's because its star is on the cooler side too. Astronomers think they've seen clouds in the atmosphere of this mysterious planet, and maybe they're even made of water. This star and planet system is moving away from Earth pretty fast. That's why scientists easily detected hydrogen atoms that were escaping from the planet's atmosphere. Yep, That means the planet may even have a tail. A hypothetical white hole is a bizarre space object that is the opposite of a black hole. It's intensely bright and was first mentioned by Einstein in his theory of gravity. Most often, scientists talk about white holes in the context of wormholes. There's a theory that a black hole is like some sort of entry point to a tunnel that takes you through space and time. In this case, a white hole might be an exit located somewhere else in the universe. On the other hand, white holes don't necessarily need to be exits from wormholes. They could also be a slow-motion replay of how original black holes were formed. So, the formation of a black hole starts with an old massive star. After it collapses under its own weight, it usually turns into a black hole. But sometimes, quantum processes don't turn a star into a black hole. Instead, they make a white hole that starts spewing out the matter of the original star again. But so far, this is just a theory. Some planets, like Mars and Venus, have pretty intense weather with powerful storms. And now, an equally strong space hurricane might have come to Earth. It was a swirling mass of air about 620 miles wide. Satellites spotted the hurricane hundreds of miles above the North Pole, somewhere in the Earth's upper atmosphere. The hurricane was raining not water, but electrons. It lasted almost 8 hours before it finally broke down. It was spinning in a counterclockwise direction. It's possible there are oceans hidden under the surface of the moons surrounding Uranus. Scientists have also been investigating the oceans on Jupiter's moon Europa and Saturn's moon Enceladus. These oceans are hidden below the moon's icy crusts. Uranus has 27 moons. 5 of them are especially big. Those are Umbriel, Titania, Oberon, Miranda, and Ariel. Back in the 1980s, when people sent Voyager 2 to get us some images of these 5 moons, scientists found out that they had lots of craters and were made up of ice and rock. Pictures astronomers got then also showed signs of liquid water. It was erupting from the moon's depths and freezing on the surface. One of the most plausible explanations was the oceans under the surface. As a moon moves around a planet, the magnetic field of that planet tugs at it. That is how the moon stays in its orbit. This tug generates an electrical current that transforms into a magnetic field. Such a magnetic field is called induced, and subsurface oceans might be the reason why this induced field can be produced. Saturn is well known for its famous rings, but Neptune, Uranus, and Jupiter also have rings. At the same time, Saturn has something really special we've never seen on any other planet. It's this huge hexagon storm moving around the planet's north pole. Each of its sides is almost 7,500 miles long. That's an area so great, we could place almost 4 Earths inside. According to thermal images, this hexagonal cloud pattern goes down into Saturn's atmosphere for around 60 miles. The planet is hiding behind thick clouds, and sunlight can't get through them. That's why astronomers can't see what exactly is going on there. But there are theories. Saturn is a gas giant. When gas deep inside the planet gets heated, it strays further out. Huge amounts of energy are released along with that gas, which makes it rise, expand, and lose density. The same processes cause hurricanes and tornadoes on our planet. On Saturn, whirling gases come out of a high-pressure zone located within Saturn's outer layers, and these gases trigger a powerful storm of such an unusual shape.
Can we power spaceships using black holes? Kinda. Exploring our galaxy is a bit problematic. Our fastest spacecraft ever, NASA's Parker Solar Probe, only travels at about 0.06% the speed of light. So it would take around 7,700 years for us to reach even our closest neighbor star, Proxima Centauri. Therefore, we need to find a way to achieve super high velocity without wasting too much fuel. Why don't we consider powering spacecraft using radiation from black holes? Natural black holes are too massive for us to harness. However, during the early stages of the universe, there might have been very small black holes known as primordial ones. Perhaps we could attempt to recreate them. In order to do so, we would need to concentrate a massive amount of energy on a minuscule point. Imagine a mass of about 1,000,000 tons with a radius of a few attometers. Scientists have devised a method to accomplish this. By collecting a vast amount of the sun's energy using solar panels, directing it towards a single point, surrounding it with collectors to capture the emitted energy, and utilizing its radiation to power a spaceship. What a brilliant plan! As for the implementation, we'll have to wait and see how it unfolds. Scientists in Japan have developed artificial wombs that can nurture premature baby sharks. They help embryos to be prepared to be born properly. These artificial wombs can power little sharks for almost a year. This is much longer than their previous record of 160 days. The invention actually works. Some embryos grew from 1.2 to almost 6 inches, which is their natural birth size. Premature sharks are very vulnerable because the seawater is too salty for their little bodies. This is especially dangerous for viviparous sharks because their young ones are born without a protective shell. So what scientists did is they put them in these containers and started slowly decreasing natural fluids and gradually increasing the seawater until babies got used to the salt. The results are still not perfect though. Out of 33 embryos, only 3 reached birth size. However, these 3 are healthy and now live like any normal baby shark. They munched on some minced mackerel and shrimp and behaved typically for their age. The end goal of all this research, of course, is to develop more universal systems for wider use. Sensing a hug over the internet might soon be possible. Using e-skin. Researchers at City University of Hong Kong have developed a wireless, soft e-skin that can detect and deliver the sense of touch. This creates a touch network for multi-user interaction. The e-skin can both sense touch and imitate it. We had similar technologies like that before, with VR for example, but not both of them at the same time. Here's how it works. You press an actuator, and it generates an electrical signal. This signal is converted into a digital signal by an analog to digital converter. Then it's sent via Bluetooth to another e-skin. The receiving e-skin converts the signal back into an electrical current and it recreates the touch sensation through vibrations. Finally, long-distance friends and family could use technology to feel each other. This technology might also help visually impaired people with directions and reading Braille messages. Now, imagine being able to 3D print literal bones. This is a new technology that helps us create synthetic bones with living cells. It uses a special ink that mimics natural bone. First, you create a model, like a custom bone design. Then the printer uses ceramic ink in a gelatin bath, extruding it layer by layer. You 3D print this thing at room temperature. Then, the printed bone material hardens and integrates with existing bone tissue, and voila! Still, there are some problems left to solve. For example, make sure that there won't be any immune reactions, make the material stronger, and so on. By the way, in Mumbai, there's a startup that has created helpful 3D models of organs for over 1,200 operations already. And the technology will only keep improving. The next goals are to add blood vessels to ensure nutrients and oxygen reach the tissue and develop smart materials that will change depending on the environment. In the future, you might have a digital copy of your body to track your health. A digital twin is a virtual model of a physical object that not only looks like the object, but also behaves like it. To be fair, it doesn't have to be a full-blown copy of you. It can be something simple, like a copy of a heart. Unlike a simple 3D model, a digital twin must show how all parts of the object interact with each other. It will show all components and their interactions, not just the shape or appearance. Looking at them will help doctors understand and improve health outcomes better by tweaking random parameters and seeing how the condition changes. For example, recently, researchers created digital twins of patients' hearts. The model showed the heart's structure and damage, things like scars and all that. They also had a simulation of the heart's electrical activity. They tried sending signals through the digital twin, looked at how it behaved, and were able to predict issues like arrhythmias. What if your walls could eat sunlight during the day and use the accumulated energy to power the building at night? Buildings literally powering themselves? Check out the energy-storing bricks. They can be built in walls among regular bricks, capture extra renewable energy, stabilize the power grid, and reduce reliance on fossil fuels. They use a type of concrete that can store electricity and power devices. These bricks can turn the red pigment in standard bricks into conductive plastic, which can store and release tons of charge. Pair them with solar panels and voila! Lots of clean energy, which also works even in case of power outage. And they're pretty affordable as well. People could also use them to create portable and flexible devices powered by these bricks, such as wearable electronics, sensors, or displays that attach to clothes and stuff. Potentially, these bricks could be 3D printed and mass-produced. China has developed a groundbreaking car battery that can get fully charged in just 10 minutes. Moreover, it could power a car for hundreds of miles before needing to be plugged in again, all thanks to recent great advancements in chemistry. Chemists found a way to store much more energy. The latest batteries can enable cars to travel 250 miles on a single charge, and newer versions can achieve up to 600 miles per charge. In the future, this could make electric cars much more efficient and convenient. You'd think it sounds nice and dandy, but there's a catch. If there are any disruptions due to extreme weather, trade disputes, or anything else, people will be screwed. It's not like you can go and ask your neighbor to lend you gasoline. Electric cars might not be able to get the batteries they need. Anyone who drives an electric car to work would be stuck, and the prices would skyrocket. There's also a weird type of battery that is made of sand. Finnish engineers filled a large steel container measuring 13 by 23 feet with 100 tons of sand. They then heated the sand using wind and solar energy. This method allows energy to be stored for months. In a battery like this, electricity used to heat air in a special system of pipes. The hot air then flows through these pipes to warm up the sand. This generated heat can be used as energy. This is called resistive heating. Sometimes, new technologies can be both amazing and a little creepy. That's definitely the case with necrobiotics. This involves turning things that passed away into robots. It might sound like a horror movie plot, but researchers at Rice University think it will be super useful. A team at Rice University has turned a deceased spider into a robot-like gripper that can pick up objects. They do this by injecting air into the spider. Spiders use hydraulics to move their limbs, forcing their version of blood into their legs to make them extend. These necrobiotic grippers could be used in delicate tasks where traditional robotic parts might be too bulky or rough.
Picture this. You're planning your dream holiday, but instead of going to a tropical beach or a bustling city, you're thinking about going to space. Imagine yourself floating, weightless, looking down at Earth from a whole new perspective. The beauty and wonder of our planet become even more evident when you're viewing it from a distance. And now, this dream can come true. Yes, you heard that right. Space tourism. Space tourism is something that has fascinated people for generations. This idea has been around for almost 20 years. We've seen it in movies and read about it in stories. But now, thanks to advancements in technology, it's finally becoming a reality. The first space tourist was a businessman named Dennis Tito. He visited the International Space Station in 2001. Sounds incredible, but here's the catch. Tito's trip cost a mind-boggling $20 million. That's a lot of money, and it made space travel seem like a dream that only the super rich could afford. And it's true that space tourism can be quite expensive. But a lot of time has passed since that day. And now, space tourism is becoming more attainable for people who aren't billionaires. Of course, the industry is still in its early stages, but the demand for it is skyrocketing, pun intended. Experts believe that it will continue to grow at an incredible rate of around 40% every year from 2023 to 2030. So, with all this in mind, let's talk about what awaits us in the near future. There are different types of space tourism. First up, we have suborbital spaceflight. It's the trip where you reach an altitude of over 300,000 feet, which is way higher than any airplane can go. In fact, it's so high that you cross a special line called the Kármán line, which marks the boundary of outer space. How cool is that? So it's basically like a quick jump into space and back. So let's talk a bit more about suborbital spaceflight. Imagine you want to go on vacation to Sydney, but you live in London. Normally, it would take you about 22 hours to get there by plane. That's a really long time to sit on a plane. But guess what? Scientists and engineers are working on a new way of traveling that could make the journey from England to Australia super fast and exciting. Suborbital space trips could be used for quick travel between different cities on Earth. Instead of flying in a regular airplane, you would hop on a spacecraft that can go really, really fast. According to a recent study, in the near future, it might be possible to fly from London to Sydney in less than 2 hours. Just imagine how amazing that would be. You would zoom up into space, see the Earth from above, then come back down in no time at all. What an adventure! This study, conducted by the UK's Civil Aviation Authority, was all about understanding how our bodies react to trips outside Earth's atmosphere. To figure this out, the researchers needed some brave volunteers. They recruited 24 healthy people between the ages of 32 and 80. These volunteers were taken to a special training facility called an RAF centrifuge in Cranwell. A centrifuge is a big machine that looks like a giant spinning chair. The volunteers were sat in there to experience a simulation of spaceflight. They were spun around, and their bodies felt the pressure and changes in gravity that happen when you go into space. Almost everyone handled the simulation pretty well and quickly returned to normal. One person even briefly lost consciousness, but it was because of the gravitational forces, and they recovered soon after. Now, this study found some surprising things. Many people think that you have to be really fit and young to handle space flights. But the research showed that older people can actually cope better with all this gravity craziness. So even if we don't develop space tourism in the next decade or two, you'll still have a chance to visit space, even when you get old. Right now, there are two big players in the suborbital spaceflight game: Virgin Galactic and Blue Origin. Both of these companies have rocket-powered systems that can take up to 6 passengers on a thrilling ride. Virgin Galactic has already had 4 successful flights, but they recently ran into some financial trouble. On the other hand, Blue Origin has flown 32 passengers on their new Shepard rocket. The catch is pretty obvious. Right now, space tourism is super expensive. Companies can charge a whopping £350,000 per seat for these flights. But don't worry, things are about to change soon. Experts believe that space tourism will grow in the coming decades. It will be kinda similar to what happened to airplanes. Right now, the cost of a quick trip to space is very high. But as time goes on, the prices will go down. Eventually, space tourism will become more affordable and accessible to people all around the world. That means not just our children, but many of us will have a chance to experience the wonders of space. As technology advances, we might even be able to plan rocket-powered holidays in the future. Can you imagine telling your friends that you went on a vacation to space? What a flex! And now, let's talk about orbital spaceflight. This is the real deal, where you get to spend more time in space. Instead of just a few minutes, you can spend anywhere from a few days to over a week up there. And we're not talking about a measly 300,000 feet anymore. We're talking about going over 1.3 million feet high. So whether you're up for a quick jump into space or a longer adventure orbiting our planet, space tourism has something for everyone. Sky is no longer the limit. But space tourism isn't all fun and games. There are some challenges we need to consider too. First off, let's talk about the environment. Launching spacecraft and rockets takes a lot of energy and can create air and noise pollution. This can seriously harm our atmosphere. We don't want to trade a cool space trip for a damaged planet, right? Next, there's the issue of safety. Space travel is still risky, and accidents can happen. Even with safety protocols in place, there's always a chance of something going wrong. And if it does, the consequences could be really, really bad. Yikes! Space debris is another concern. Every time a spacecraft is launched, it leaves behind debris that can stay in orbit for a long time. As more launches happen, the amount of debris keeps growing. This can cause problems for other spacecraft, and even small pieces of debris can cause damage. Space travel also requires a lot of resources like energy, fuel, and materials. Using up these resources too quickly could have long-term consequences for our planet and future generations. We need to make sure we're not depleting everything in our quest for space exploration. Oh, and let's not forget about all the legal stuff. The rules and regulations for space tourism are still evolving, and it's not always clear who should be responsible if something goes wrong. Plus, there are concerns about how space tourism might affect international space laws and treaties. We don't want legal chaos in the final frontier. And finally, to achieve our dream of taking spaceships like planes, we'll need better infrastructure and logistics. We'll need to build more spaceports where spaceships can take off and land. But don't worry, scientists are actively working to solve these problems. Remember, it's not just us who are excited about space tourism, even governments are joining the fun. Many countries are investing in space tourism too. It's a global phenomenon. So even though there's still a lot to develop in this industry, it's pretty obvious that the aviation industry might go through a big revolution. Traveling long distances would become much quicker and more exciting. And judging by the way development is going, the first big breakthrough in this area will be made in North America. So, get ready for a new era of travel. What an exciting time to be alive, right? The universe is calling, and it's time for us to answer. Stay tuned!